So hi everyone. We are going to solve a 2025 question paper, sorry, 2024 question paper. And before starting, I would like to just reach every one of you. So if you're watching this video, do like to peer our scholarship test. So basically, the idea is to help at the cost of merit. So if you perform well in the test, accordingly, you'll be awarded from 25% to up to 100% test. And most of the students usually fall under 50% scholarship or 75% scholarships. That's the overall motto to help you all. Okay, so let's start the solution. So if you see, so we are going to see XCC material science first. If you see the question number first, that is directly from the water phase diagram of H2O or water. Okay, so it's a quite it's not no brainer. Okay, so if you understand basic isomorphous phase diagram or a basic what you call it simple phase diagrams of binary systems, so unary is not a brainer. Okay, if you know water, okay, so if you can't understand the phase diagram of water, it's very difficult. So everything starts from water or unary diagram or even phase diagram of pure iron as well, right? So if you see here, I mean, if you don't, I mean, if you've not ever uh, uh, read about it, okay, but still you'll be able to solve it. So usually, so you in water you have a liquid phase and then the solid phase and the vapor phase. Liquid phase means water, right? Water that we know, and solid phase is like ice that we know, and gas phase is like vapor, right? So water, ice, and vapor, these are the three. So if you decrease the temperature, at lowest temperature you get ice, right? So that is your alpha. So alpha is your ice, right? Very simple. And if you increase the temperature, what will happen? Right? What will happen? So if you increase the from ice, if you increase, okay, so either it will become from ice, it will become liquid, and then from liquid it will become vapor, right? So vapor. So typically at higher pressure, this is your 1 atmospheric pressure. This is your 1 atmospheric pressure, okay, and this is the typical melting temperature. With respect to atmospheric pressure and with respect to melting temperature of water, okay, you'll get the liquid phases here. So you always get, if you increase the pressure, okay, if you increase the what you call it if you decrease the pressure, okay, then your ice can directly become vapor, okay, without giving much temperature. So at low pressure, okay, and that is very usually we observe when we go at higher places like mountains or any peak places, okay, the pressure gets reduced because the amount of gases or air is lower, air concentration or oxygen concentration is lower at higher heights. So in that case, the less number of gaseous molecules means less pressure, okay. So if you go at higher places, it's very easy to convert this ice directly to vapor. That's the idea, okay. So gamma is your vapor and beta is your water. If you simply don't remember your basics, okay, you can easily answer this question. And then after that, this question is very easy. So it's the nature of basically material. So how does polymer behave, ceramic behave, composite behave, okay, metal behave? So it's a mechanical behavior of all materials. If you open the syllabus, it's a clearly mentioned like mechanical behavior of ceramic, polymer, composite, metals, okay. So it's obvious that you should know the ceramics are quite brittle and very hard, okay, and it's a no brainer, okay. Now question number 46 is the DSC. So in our test series as well and in our regular batches as well, we have discussed in great detail about different factor affecting TGA, DSC, DTA, and how the exact principle works under DSC. So what exactly you measure in DSC is heat, right? So you are giving typical in watt per hour heat, and then you're saying at particular what do you call it temperature, if there will be sudden change in heat flow, heat flow with respect to sample and with respect to reference. Okay, so you have a reference pan where you have a standard sample for which you know the behavior, how heat flow works, and you have a sample pan where you have kept your sample. Okay, and you're recording the signals from both together. Okay, so you're recording this also and this also. So if so we are measuring the difference between both. Okay, so if let's say certain heat flow is happening reference, if the exactly same heat flow is happening at sample, the net is the difference. So its name is called differential. Okay, so difference is net is zero. Okay, so there will be always net difference because your reference is different material and your sample is different material. So your difference is net, that is called a value. Let's say it is a 10. Let's say it is a 10. Okay, so if you keep increasing the temperature, what will happen? So if you keep at particular temperature, let's say at 25 degrees Celsius, you measure what is the heat content in sample, what is the heat content in reference. There will be a difference. The difference value is, let's say, this value, that is the 10. Okay, at particular time, of course, we are heating at a particular rate, so heating rate also matters. So we fix the rate, at particular rate we are heating, so difference is 10. Now it difference will keep maintain because your material has certain heat content, heat capacity, as well as what do you call it, thermal conductivity. So based on that, heat will flow inside it, so the difference will be same. The moment you get certain transformation or transition in your material, suddenly there will be change in heat flow. So if it is 10, continuously constant 10, it will become lower or higher depending on which part is your exo, which part is your endo, means which part is showing the heat absorption, which part is showing the what do you call it, removal from the sample. Okay, so you get a transition and then you get particular peaks. So basically we are measuring what? Heat. Okay, so weight change we measure in TGA, right? And vapor pressure measure in osmometry. Entropy is not measured, but of course you can plot an entropy versus T. Okay, so something like this you get for glasses, and something you get for crystals, right? So this we know, like S, V, and H, all three can be plotted with temperature. And basically we do it with the dilatometry. Okay, dilatometry. Using dilatometry we can see what is the volume change with the temperature. And this is for glass, where this tangent will give you the TG, and this is the typical melting temperature. Before that they are viscous or liquid, before they become solid. So this graph we know. Okay, so it's a standard graph that we use for TGTM and entropy, or even second order or first order transition explanation that we give. Okay, so the entropy is something that is plotted in dilatometry. So it's a heat. It's a no-brainer, and you all can easily understand it. And if you want to learn more about this, you simply know which graph is plotted using, I mean, what is the graph exactly plotted in particular equipment. If you remember the graph, you can easily plot it. Right now, next one is the in ball milling ceramic powder. So it's a basically ball mills that we use to generate nano what do you call it, powders, or even making the ceramic powders. So in powder metallurgy, it's quite obvious. So we have atomization technique, we have ball milling, that is the grinding, I mean, using the powdering or grinding of the sample. Okay, so basically our ball mills, what we select is based on the hardness. Okay, hardness of the what, I mean, which ceramic you are going to use for making powder. So what is the hardness of the ceramic? Depending on that, we select, I mean, what will be the ball and its quality, right? So its hardness is something that is important because they are going to have a lot of wear and erosion, right? So that is very important. Now, so which one of the following unit cell parameter represent tetragonal? So it's a very simple logic, right? So all is 90 degree, and the C is quite bigger, where you maintain C by A is root, I mean, 1.633, right? So it's a obvious question, or based on memory. Which of the following types of material exhibit polymer positive magnetic susceptibility? See, before this GATE 2024, I shared the same test series material, right? And each slide that is given there are so condensed, you have to memorize it at any cost. Okay, except the polymer rheology, because we have covered a lot of slides on polymer rheology to develop understanding. But in material science notes, test series notes, if you see, I mean, there is a particular points to remember, and this notes has been and we have been sharing it for last three years, right? So if you see that if you see that notes if you see that notes, I mean, test series notes that you all have, I mean, we have shared to you all. We have given different materials, right? And if you see this, we have specifically for mentioned what are the magnetic properties of metal, what is the important things to remember, and this was shared last year as well, and the year before last year as well. If you see the first slide, it is mentioned all the condensed form that you need to remember, and they can always frame one question from this. Okay, so if you see this, it is a magnetic susceptibility. For diamagnetic, it is negative and small. For paramagnetic, it is positive and small. For ferromagnetic, it is positive and very large, right? And for anti-ferro, it's positive and small. For fairy, it is positive and large, right? So it's a positive and large. So it's a simple understanding that you need to develop. That's it. Okay, and then of course how the curve behave is also important. What is the, I mean, typical critical temperature like Curie temperature or Néel temperature, right? Or these are the temperature we measure in what kind of material, whether paramagnetic or ferromagnetic. This is a thing that you need to remember, right? So they can make always one question, right? So that's obvious. Even this table tests the same thing. Like paramagnetic, see, your chi is positive, ferromagnetic chi is positive and very large. Okay, so it was given many times, and but still some of my students did the mistake. Okay, even the mind map is given to you, you have to memorize them at any cost. There's no alternative. Okay, you have to memorize them, because they can always make one question, and see last year they made. Okay, so for magnetic material, whether it is in the absence of H, whether it is magnetic or not, you divide it based on that, and then depending on the this can behave magnetic if there is present of magnetism, but if there is no magnetism, it is simply non-magnetic, right? And then you see the ferromagnetic, it has positive chi and very large chi, and diamagnetic, it's a positive and negative and very weak. So these are the things that is already given, even with lines that is made to help you memorize it. Okay, so examples are also very important. So it was already given to you all, and I hope hopefully I mean, some of students was correct predicting this answer, and some were not. So that's the story. Okay, so paramagnetic, small and positive, and fairy and ferro both are what you call it, large and positive, of course. And it's very understandable, right? If you, so what is susceptibility? Susceptibility is how susceptible it is, okay, to the magnetic field. Means if there is a magnetic lines of forces randomly oriented in the particular domain. Okay, now if you apply the H in this field, how susceptible, or what is the ability to sense this H and react to it, respond to it, that is called susceptibility. If it is large and positive, that means a very high magnetic material. So fairy and ferro both are very high magnetic material. We all know fairy because of the spinel structure, where there will be net magnetic dipole magnetic movements, right? The spinal structure that you remember, if you that we have learned in the test series, right? And ferro is permanent dipoles, and there will be the permanent magnetism, right? Para is small, because if you apply H, they will try to align themselves. Okay, so this is the way you remember each and every slides that is given in the test series. Okay, that is very important. Each data that is given in the test series notes. Okay, and each question that is given in the test series, that questions was in the test series. Okay, now next question is pitting corrosion. So different forms of corrosion is there, and you have to understand the definition of each form of corrosion. Okay, whether it's crevice, whether it's pitting, whether it's galvanic, you have to understand the examples as well, and what is the factors that will affect that kind of means what is the ideal scenario where this form of corrosion will occur, and what is not. That comes in the definition itself, right? So what is pitting? Pitting means if there is a scratch, or if there is a particular mark or dent, right? Indent, that is where there will be a high concentration of energy. And if you see the typical reactant versus product, which is the free energy versus the organization of atom, or position, whatever you say, or state you say. So you see, this is a typical curve that we know, that there is a reactant, or present material, and it wants to become this final material that we call it product. To become from present material to final material, it has to it needs certain energy, right? It needs certain energy. We call it energy barrier. Okay, we call it energy barrier, and that energy barrier must be given. Okay, this is the energy barrier delta G star. This is must be provided to overcome this barrier. Once this system will come here, it will naturally go and become product. Okay, so this is the barrier, energy barrier, that is required. Now what happens if there is already existing energy? What happens if so how what happens if there is, for example, let's say there is a coal. Okay, there is a coal. It wants to become ash, right? And to become ash, you have to burn it, right? So this is the reactant and this is the product. Now to burn it, to start burning, you need to give certain energy to it so that it can overcome the barrier and start burning, right? So that barrier is it's a typical heat that we provide in form of fire to it. Okay, and the moment we provide heat, it becomes hot, it starts burning. Okay, so the barrier we provide. In the same sense, if a steel wants to corrode and becomes, if iron wants to become iron oxide or iron OH form, iron hydroxides or different hydroxide forms of iron, it has to give certain energy. You have to give certain energy. Okay, that is a barrier that is required. It not natural. Okay, so of course corrosion is spontaneous process. Even if you don't give any energy, it will naturally form. That means it has very high, usually your reactant is here and your product is here, but it is naturally very high energy state, because naturally it was iron ore and then it was reduced to become iron when it is in the steel making process. So we already have high energy state product. Okay, now it will naturally, so from this it has already converted into high energy state, this, right? Now it has already, you have already raised it, you have slightly raised its initial energy states to higher energy states. Now it is more easy to form product. That's one thing. But even you can accelerate the corrosion if you can even raise this bar. If you can even raise this bar to make it go slightly higher. Okay, like this. Now your barrier is, let me remove everything. So this is the naturally this is the material that we have currently, and we want to make this material. Now imagine iron. Now you have already raised it and make it like this. So initially your energy barrier was this. Okay, now you have raised it and now your new energy barrier is only this much. Okay, so your iron will naturally corrode. Okay, means you need iron needs very small energy to start showing the corrosion or oxidation, right? And now when you have an indent or a scratch or certain localized deformation, what will happen is that position you already generated a lot of dislocations, plastic deformation there at localized form. So there you have a lot of dislocations that has entangled, and those dislocations will have their corresponding associated stored energy. So there is always stored energy per dislocation. We call it, what you call it, GB square, right? Half GB square. So that GB square stored is energy with every dislocations. Okay, so this you need to understand. So even in hardness testing, what exactly we measure means, if you see hardness of any material, and if you see the, what you call it, ys of any material, right? Or any strength form. Okay, you see usually if a particular factor that increases strength, it also increases hardness, right? If you see this, if you see the precipitation hardening, this is how the curve goes, right? So you have a theta double, you have a GP zone, then theta double prime, then theta. So your hardness increases with the time, right? Because the precipitate starts growing and becomes a optimum size of precipitate where hardness is maximum. So this is hardness. You can also write strength. Even with the concept, this is a precipitation hardening. Even in the grain size reduction hardening or grain refinement hardening, the smaller the grain size, the stronger material becomes, right? Your ys is what? Ys is sigma naught, the ys is inversely proportional to d, right? So the Hall-Page equation. So lower the size, higher the yield strength. But at the same time, if you lower the grain size, your hardness also increases. So hardness and YS is very analogous, right? For example, if you see the Brinell hardness number is 3.45 times uh, UTS, right? If I'm not wrong, or whether it is reverse, UTS is 3.5 times. No, BHN is 3.45 times UTS, right? If I'm not wrong. Yes, guys. Brinell
Yes, sir.
hardness number, yes. So Brinell hardness number is 3.4 times UTS. Okay. So see, your hardness increases with UTS. Why it's happening? Why it's happening? That's why. So from dislocation, I diverted to this topic to make you understand. Okay, the fundamentals. Okay. So hardness and the UTS and the what you call it behaves or strengthening with precipitation behaves similar way. Why is that happening? Is when you're measuring the strength. Why says what is happening is uh, the more obstruction to the dislocation motion, more the strength. It's very easier dislocation can move on the slip plane, the lower will be its strength. It's very easy. The moment you stop this dislocation to move, like you created one precipitate here, dislocation will start move, then it will start bowing, and then it may cut also, or then it may cut also, right? Or it may just bow it, and it can make you the loop along that precipitates. Okay. So you are providing precipitation in the path of dislocation motion, and once this dislocation motion is obstructed, your strength shoots up, your strength increases, right? So same idea is with the grain size hardening or the grain refinement. Smaller the grain size is, bigger the strength. Why is that happening? Because every grains, if the dislocation will move, it will start piling up at the grain boundary. Why? Because there is every grain boundary is a collection of screw dislocation and edge dislocation, right? So whether it is a twist boundary or tilt boundary, it will be either of the area of screw dislocation or edge dislocation, right? So there are a lot of dislocation along the grain boundary, so it has to jump, it has to change the slip plane. So it has to jump from this to this, and to jump this grain boundary, you have to give extra energy, extra strength, and that is how the strength is increased. Every grain boundary is acting as a obstruction. We call it grain boundary hardening. So what exactly fundamentally we are doing is, we are actually stopping the dislocation. Now if there is many dislocations together, two dislocation of opposite side can come together, but two dislocation of same nature, they will repel each other. So many dislocation start entangle, and they entangle into in such that it's very difficult to move. This is happening in strain hardening mechanism. If you deform material, deformed material will become more harder, more stronger as compared to the less deformed material. So with cold working, your material become harder and stronger. Why is that happening? Because of the entanglement of dislocation. We call it dislocations. So see, the dislocations are something that is actually stopped, so that strength is shooting. In the same sense, in hardness also, if you apply, so how you measure the hardness? Measure the hardness is nothing but the resistance to localized deformation, or resistance to indentation. So when you indent your material, okay, with the diamond tip or steel ball tip, okay, so how bigger the indent that you're forming, the diagonal will define the hardness number, right? So bhn is what? Force. There is a factor here, force divided by L square. So bigger the this diagonal size, lower the hardness. Why? Bigger, when this diagonal size will be bigger, when it is very soft, material is very soft, then more bigger the notch will be generated, right? And that means material will be lower hardness. So what is happening? Why this resistance is somehow correlating with the strength? Resistance is hardness, and why this hardness is correlating with strength? Why is that happening? Because at the localized level also, we are doing the deformation only. The pit that you're developing, you're generating the deformation only. Now to do any deformation, whether it is at micro level or macro level, level or micron level, the dislocation needs to move, so that you see some plastic deformation, permanent deformation, whether it is just a small indent or whether it is a big plastic deformation. So in that sense, you have already dislocated the you have already what you call it moved, forced the dislocation to move. And if the dislocation will move, they will entangle, right? And they will entangle and they will stop moving, and that is where the material is showing the resistance, because dislocation is no longer move for at particular force, right? So it's no longer able to move. That is how the resistance is calculated. So actually it's a movement of dislocation, resistance to the movement of dislocation. And in strength also it's the same, resistance to the movement of dislocation. That is why hardness and strength is correlating. Now my question is, why I'm discussing all this dislocation phenomena? Because your dislocation is carrying stored energy, and that is very important. Dislocation is carrying stored strain energy, because that dislocation fundamentally is nothing but the defect, right? So your material is distorted along the dislocation. Here they are closer to each other, here they are farther to each other. So naturally currently they are forced to move inward. That means naturally they want to go outward. That means here it is a tensile strain, and here they are forced to go inward. That means uh, uh, they are forced to go inward, okay, but that means they wants to go outside, okay. That's a tensile, and here is a compressive strain. So there is a strain associated with each dislocation, and that strain is carrying stored energy. So that is where I come here. So why that rough surface or grain boundary or any indent enhances the corrosion? Because to start any corrosion, everybody wants to minimize their energy. So this steel wants to minimize their energy, right? This steel wants to minimize their energy. So it is here, it wants to come here, but to go there it has to minimize the energy, right? It has to overcome this barrier, and this barrier is given by the indent that you created. This indent is carrying the dislocations and that dislocation is having a stored energy. That energy is enhancing the somewhere like this. You have raised the energy state from this to this. Now there is a no barrier or very small barrier. Now it's very natural to start forming the oxide or the corrosion, and that is why this indent, this rough surface, scratches or indent or any design where there is a corner, that is where there is a residual stress or strain energies associated with that localized deformation, and that is where the pitting starts happening, because you have given the energy to the activation energy required for the reaction to happen. Okay, so rough surface is something that is naturally. Now grain boundaries is also the same thing, right? It is a localized form, because each grain is giving you what? Each grain is giving you a triplets, and that triplet there is a in that triplet, if you remember my test series classes, you might be knowing that we get a groove on the grain boundary triplets, because there is a net force imbalance, net force imbalance of surface energy associated with every grain boundary, because grain boundary is nothing but a 2D surface. So every surface have a energy, surface energy. Why? Because each on the surface there will be no broken bonds, okay, because inside the material each atom is satisfied with the bonding, but on the surface one side is broken, right? So that is why there is an energy, and that net energy is also the grain boundary energy. On the triplet you got a net non-equilibrium or net energy associated in certain direction, and that is where the pitting starts happening. We also get intergranular corrosion, but that is also one form. Okay, so that is something that you must understand at the fundamental level to answer this type of question. You cannot read this in any book. Okay, you have to understand the concept to give the solid answer. Okay, now next is very obvious, that what are the different factors that will affect the TGA or even DSC. Okay, so it's very important for you guys to not just understand the graph, but how this graph can change if I change the factor. That is, this question can be easily solved if a student is continuously practicing or doing the characterization or testing. So if you do the thermal testing or typically DSC or TGA, you very much know what are the factors in the standard that is given. The standard typically typical ASTM standard or IS standard that you know, no? ISO standard, it is fixed that you cannot change heating rate. You have to fix the heating rate because heating rate affects this graph. If you change the heating rate, this graph will be changed. Now it also says the initial temperature is also one factor, the size, or so what are the different factor that is given in the standard. But if you have not read the standard, because not you're not performing testing in the laboratory, you have to read it very carefully on any testing. All the testing you must learn what are the different factors that you have to keep same to compare the two readings of two different materials. Let's say you have made three samples, okay, S1, S2, S3, by adding some composition. Let's say you have added fibers, okay. If you have added fibers in your polyethylene, so you made composite. Now you want to make the DSC, and you're testing it in a TJ, DSC, or any kind of, even in the UTS, I mean UTM machine. You have to know what are the factors that you have to keep same, like room temperature. You have to do at room temperature or same temperature. You have to have the same sample size, because if you change the sample size, your elongation and what you call it, other mechanical properties may change. So there is a fixed standard size, right? So sample size is also one factor, and also strain rate, at what rate you are elongating, and in case of this, what is the heating rate that you're giving. So there are many factors that you need to learn, okay. If you have not read it, you please read it, okay. It doesn't take more than 10 minutes to learn for each testing. So testing of polymer is very important here, and fortunately all the testing of polymer also comes in testing in the materials, right? So that is the same thing that you can learn for both polymer and material. But I would like to give a few graphs to give you a sense, because I don't want you to go again and read, because you will start searching in different books. I'm going to give you all of it right now, so you don't need to read, because I know your exams are very close. So I have one PPT there, so let me share that PPT. Oh, so this is just a, PPT that is. Let me open another PPT. Hmm. So the answer is, doesn't matter how these factors are going to affect, matters a lot. Okay. So my screen is visible right now. Oh no, my screen is visible right now, right?
Yes, sir. Yes, sir.
Okay.
It's visible.
Yes, sir.
So not going to. Okay, not problem. Okay. So next one is, okay. So okay, so this is typically the TGF. You need to understand that I'm not able to fully focus it, because it's again sending back to the first slide. Just a second. So okay, so if you go in the second slides, okay. So first of all, it's very important to understand, okay. So TGA curves are not fingerprint curves, okay. So that means most of the events that you see, no, like typically the volatile matter that is getting evaporated, that means you're getting the weight loss at particular temperature, okay. So there is a weight loss, net weight loss in each transformation. So they are kinetically happening, okay, occurring. So by nature, they are kinetic in nature, okay, each events. So that means you cannot reproduce it at every factors, like it at every in every sample size, in every heating rates, or in every particle size, okay. So there are many factors that may affect. It's not fingerprint, like every time you'll get the same result. Doesn't matter in what conditions you're applying. Like for example, in even in what you call it, FTIR results, or UV visible spectroscopy results, right? The graph that you see, the peaks at particular bonding, like carbonyl functional groups peak that you're getting around 1700, it's always 1700, right? So but here, if you change the factor, you'll get different graph, okay. So the factors that is important here are the heating rates, sample size, particle size of the sample, and crucible shape and size, gas flow rate, and chamber atmosphere or gas type, okay. That means pan material, shape, size, ramp rate, purge gas, or sample mass, or volume, form, or morphology. These are the important factors in DSC as well as in TGA, okay. So if you see, so okay, so you see here, heating rate. So if you increase the heating rate, okay, you see this, how graph is slightly shifting towards the right side. Okay, so if you change the heating rate, you're shifting. So you have one graph at 2.5, you have one graph at 2.5 Celsius per minute, then 5, 10, 20. You see, it is shifting towards the right. So why is that happening? That you need to understand. Okay, so if you have very high heating rate, what will happen? Because you're not, if heating rate is high, that means heat, the time that you're giving for heat flow is low, right? Right? Heating rate is what? Heat given per unit time, right? So if heating rate is very high, that means you're giving very small time to flow, right? Very small time. That means if very small time, that every molecule has to absorb that energy, right, to transform. So if it is not getting time to observe, how it will transform, right? The volatile matter that is there, let's say in moisture, how that moisture will vaporize, okay, because you're not giving time, right? So that moisture takes slightly more temperature, right, slightly more temperature to vaporize. So this, let's say this is a moisture drop that is happening at, let's say at around, this is of course not moisture drop because it is around 500 degrees Celsius. I'm just giving one example, okay? So the transformation that is happening, it happens later. It takes some certain more time, okay? More temperature. More time is more temperature means more time. Because if let's say it is 10 degrees Celsius per minute, to reach 100 degrees Celsius additional, you need 10 minutes. So let's say you are 500 and the reaction will happen at 600. So to reach from 500 to 600, see, it's a 10-minute time, right? 10-minute time. But still, a 10-minute time it takes to vaporize. But at the same time, if you are giving 20 degrees Celsius, so that temperature will be reached in 5 minutes, but it requires 10 minutes to transform, right? The kinetics of that reaction is requires minimum 10 minutes. If you are giving 20 degrees Celsius per minute, the temperature will be reached in 5 minutes. But it needs 10 minutes to complete that reaction, because every reaction is kinetic, right? There is a kinetic involved in that, how fast the reaction happens, right? So that is why it keeps shifting towards the right if you keep increasing the rate, because it needs time kinetically, right? So it's a very what do you call it, intuitive to understand, right? Now if you increase the heating rate, it shifts to the right. That is the understanding that you need to develop. Now, what is the effect of sample size or on decomposition temperature, right? So sample size, if you see, so usually if the sample is very small, very fine, then what will happen? It's all about the heat flow, right? So heat flow, if very small and if it is very big, okay? Now tell me, which one will have higher surface to volume ratio? Which one will have higher surface to volume ratio? See, smaller it becomes, S by V ratio becomes bigger. Okay, it becomes bigger. Why it becomes bigger? Because volume is becoming smaller. Because size is smaller. So volume is smaller. If volume is smaller, okay, then S by V becomes bigger. Let's say it is N. So if volume is smaller, that means N becomes bigger, right? So S by V ratio becomes, so it has very high surface to transform. And this heat flow is happening in terms of what? There is a conduction involved, right? There is a convection involved, right? And there is a, what is the third form? Radiation involved, right? So if higher surface, it gives a more conduction, right? It's the Fourier's law of heat flow law that you know. What is that? Q equals to Srimati, right? SM delta T, right? Q. So, what is that?
Q equal to MC.
Q equals to temperature gradient dt by dx, and of course K, right? And you need A also, or you can shift here. So you see, the Q heat flow is higher, the A higher is the flow. It's a simple, like if you want to cool your water, it's easy to cool in bigger plate rather than cooling in the small glass, because more surface area, more transfer, right? It's a common sense, or it is given by the law also. So more surface area, more heat flow. So that is why a smaller size will give different result as compared to bigger size, because bigger size has a lower surface. It's a common, it's a basic understanding that you need to develop, right? So it also impacts, you see, it starts shifting towards the right. Okay, now because smaller the size, more efficient the heat flow, more efficient heat flow, more faster the heat is reaching a particular molecule. That means molecule needs lower time to evolve or transform. So it's a common sense. You just sit once and start doing reasoning in your mind, you'll understand, okay, why it's happening. I have already given the mass effect. So mass effect, usually it gives very small edge if most of the sample size if you're, let's say your pan, this mass is overall mass, not individual particles mass. Otherwise, you will confuse with size. Okay, so this is not individual particle mass; it's the overall mass that you're putting in your sample pan, and of course there is a reference pan. So overall mass, how does it impact the DSC or TGA? Okay, so overall mass, so usually it doesn't affect much because we don't we usually put the mass depending on how big my crucible is, right? How big my crucible is. So usually we don't play with the mass. There is a certain amount of mass that you can put, and it doesn't make sense to all, because each mass has certain heat capacity, heat storing capacity, or heat specific heat or heat capacity. Okay, so it doesn't. But if there, it is really big that it is affecting the crucible, of course it will impact, right? So in certain reasonable range, it doesn't make sense, or it doesn't give much effect, because of course it is decided by the crucible size, and in the crucible size, whatever size you put, it doesn't matter. Okay, now as a overall, what is the sample weight that we learned? Now pan geometry means the crucible geometry, flow rate, and sample morphology. Sample morphology will impact. Okay, so you just pause that video and you see that this is typically the different weights. Okay, and samples with different weights in milligram, of course, so we are not changing much. And you have a different sample weight and difference. You see, it's not different, it's not much change. But if you go further slides, so overall, you see your heating rate is affecting, heating rate giving the shift towards right. Furnace atmosphere is also important, because that is where you start, if there is a gases involved, they can react at higher temperature. It can give more byproducts inside your final, so it will affect, of course. Sample pan materials, how, whether it is smaller size or bigger size, that is also important. And gas flow rate, at what rate. So the effect is already given here. Please read it, okay, and make a note so that you can revise and you can go before the exam with your notes. Okay, so overall particle size is important. Moisture content is important, because that will give you the initial weight. Okay, and so heating rate, it will increase. Okay, and I mean, if you, okay, so another thing is, what is the effect of heating rate on onset of Ti and Tf? Okay, so it's very important, huh? So onset of Ti and Tf matlab ki, when does it started and when does it finishes. Okay, so that is onset. Let me give you the onset concept. Okay, so this is onset. This is the onset where it start decreasing. Okay, okay, and when I mean, this is the Ti where it starts decreasing, and this is the final, that is the Tf. So this Ti and Tf will be impacted by the what do you call it, rate, right? More 10 minutes, it requires kinetically for any reactions to happen. If your flow rate is same, then this Tf will be lower, right? If flow rate is high, this Tf will go right. So onset, effect on onset is nothing but when does it starts and when does it finish. That's all. Okay, so it's the same idea that we have learned in the graph. So if you heating rate on TITF, so if you increase the heating rate, okay, so it also increases the TFTI. It's a common sense, means later onset of TI. Okay, faster decomposition, and that means the this decomposition becomes very steeper if you're increasing the, what do you call it, uh, if you're increasing the decomposition faster. Okay, that means the reaction is happening at a very short time. What does it means if you are giving the faster decomposition, means if you are increasing the heating rate, that means you are giving more heat. Okay, increasing the temperature, higher temperature, reaction will be faster as per the RNS reaction rate, right? Rate equals to K e to the power minus Q by RT. So by, if you increase the T, okay, your rate will increase. It's obvious. Okay, so we have one question based on this as well in this gate question. But the idea is, higher the temperature, higher is the reaction, because you're giving more heat, lower activation energy. Okay, it's a common sense, right? So faster decomposition, if faster decomposition, the this onset is start and final, so the delta T will become smaller. Okay, so that is the idea that is given here. And if you decrease, what will happen? More broader the decomposition range, and onset will be earlier, and but it will shift towards right. It is obvious. Okay, now chamber temperature, what is the effect is given here on TITF. And particle size of I have already given you. A smaller particle will decrease TF. Why? Because more heat transfer will happen. Okay, and decrease TF means what do you call it? More quick. Okay. Now the initial weight within reasonable range. Okay, so very minimal effect. Okay, very minimal effect, and because it depends on the crucible. So that's all. Okay, so I hope you understand. So in the short, what if I want to say, I mean in short, what is the net effect? Okay, so heating rate. Okay, so it's asking that Ti and Tf. Okay, so it's unset only. It's asking that which factor will influence Ti and Tf. That means start and final. So start and final is nothing but your whole curve, right? It means it is going to affect your curve. It's very simple. So heating rate is going to affect your curve, and particle size is going to affect curve, and our atmosphere is going to affect curve, right? If you have a more atmosphere that can absorb energy, then with the lower energy will go to the sample. Then it will absorb lower energy. That means it will take more temperature to what do you call it transform, right? So atmosphere is important, as we saw. So this is three. Initial weight is not important because you always put a sample with a reasonable size depending on the size of crucible. Okay, I hope you understand this idea and understanding. Okay, now this is the most simplest question that one can have. We used to solve this question in gate in 11th and 12th physics. Okay, so if there is a typically if there is a PV curve and if there is a circle. Okay, what will be the what do you call it work done inside it? So what is the work done? So Pi is same and Pf is same and Vi is same and Vf is same. In that case delta V becomes 0. So your work done is what is that? PdV, right? PdV. So P delta V, right? So this is your work done, right? So if your pressure is constant, so in that case delta V is 0, that means whole is 0. And also it is given by graphically, it is proved that area under the curve is work done. So if let's say if the graph is something like this, then how will you find out the work done? So the work done is nothing but area under the curve, means integration, right? Work done is integration, right? So it's very simple. So your V is your X and you're integrating it. So area under the curve. So you find out this area and this area, and that's it. Okay, that will give you the total area or work done. So it's the same as the concept of that we know it, calculation of toughness. So stress and strain. What is the toughness? Toughness is nothing but area under the curve. So you find out this rectangle area and this triangle area and you add it, you get the toughness. The same way in PV, because ideally the dW is PdV or W is integration of PdV, right? So that is why it's the area under the curve, and you find out the area, that will be the work done. It's a basic understanding. Okay, so but only thing is you need to understand the unit. So unit is litre-atm. So what is the area here? It's nothing but length multiplied by weight, right? So length is atm and width is liter. So your answer will come in naturally atm liter. And those professors who said this question, okay, they were very lenient. They give the same unit. They could have asked in what do you call it joules, or in let's say in terms of calorie, or in some other unit, but they asked a simple liter into atm. So they just wanted you to ask, what is the, do you understand the concept of work done in different processes, like in isobaric process, in isochoric process, in isothermal process? Do you know the formula for each process? Or if you know the formula, do you know graphically as well? Okay, that is the idea. So in isobaric, where pressure is constant, if you have PV, just find out the area under the curve. In isothermal curve, if temperature is constant, so that means you are changing the what do you call it so it will be somehow ln v2 by v1 or p2 by v1. So in terms of p1 p2 and v1 v2, okay, the formula is there. Okay, and that's also area under the curve only. So find out it and you'll get your answer, right? So what is the width? Width is 2, and what is the height? 2, and what is the width? 6. 2 6 is 12. Answer is 12. It's just within second you can solve. Okay, so it's funny that they have asked this. That is why ISC Bangalore focused more on concepts rather than difficult calculations, because they want you to answer the concept, not the difficult calculation. And this is true for every IITs nowadays. Okay, they are even giving you the formula. Just apply the formula, give me whether you know the concept or not. Okay, so this is the typical question that is directly given from our test series. And this question we have given in last 3 to 4 years, every test series. Like if they will touch thermodynamic questions from your syllabus, most likely they will touch the phase equilibrium of material part of thermodynamics. If they will touch the applied thermodynamics, the concepts like law of thermodynamics, the engine or the efficiency or the what are different processes like isobaric work done in different processes, concept of entropy, enthalpy. If they will go in the concept, then they will simply ask a question based on a formula or a graph. Simple. They will not go beyond that. Okay, but most probably they will ask the question based on your phase equilibrium in materials. There is a course in YouTube. What you call it? There is a course by B.S. Murthy, or there's a professor. Okay, yeah, B.S. Murthy. No, there's another professor on YouTube. Okay, there is a special course, phase equilibrium in materials, NPTEL course. You just simply watch 1 or 2 lectures in that course. You'll find this concept very easily. Okay, so idea is very simple: how to draw GX curve, how to draw GT curve, and if you know GT curve, how to draw GX curve, and if you know the GX curve, how to draw the phase diagram. So every phase diagram is drawn from the GX curve only. So what is the relation between them? That is the in the phase equilibrium of material is something that is taught. Okay, so I'm gonna give you a quick understanding of this. Okay, and it will be fit in your mind till your gate exam. Okay, so please understand very carefully. So what is the phase equilibrium of materials? So phase equilibrium. So equilibrium means the G value of particular component, okay, is going to be same. G value of particular phase is going to be same. Like GL and GS is going to be same. In the same form, if you want to write in terms of chemical potential, because G is chemical potential if the number of moles is same. So dou G by dou N is your nu, right? So your chemical potential is nothing but G at constant N or at a unit number of moles. Your G is mu. So same concepts can be given in terms of mu. So your mu of particular element A in solid should be equal to the same chemical potential of the different element in the same phase. So phase is same, individual elements chemical activity or chemical potential should be same. That is a solid and liquid criteria for equilibrium. Like two element A and B, if you're mixing, let's say copper and nickel you're mixing. Okay, this copper and nickel atom will be freely miscible into each other and they will show solid phase. Or this copper atom and nickel atom, they will be miscible and freely involved to make a single phase called liquid phase. That is only possible if chemical potential of this copper and chemical potential of this nickel should be same. The chemical activity should be same, then only they will be comfortable with each other. They will be equilibrium with each other. In what phase? Either in liquid phase or either in chemical potential of copper and chemical potential of nickel should be same in same. Okay, and they will make either a particular phase. In what phase? In solid phase. So in solid phase, their individual activity, chemical potential is same. In liquid phase, their individual is same. For individual phase, the free energy of liquid should be same as free energy of solid for liquid solid equilibrium. For let's say different alpha and beta liquid, alpha and what is the अल्फा बीटा ठीक है अल्फा बीटा लिख देते हैं फॉर अल्फा बीटा इक्विलिब्रिया योर फ्री एनर्जी ऑफ अल्फा शुड बी इक्वल टू फ्री एनर्जी ऑफ बीटा if then only both phase will be in equilibrium means they will stay together in the both phases will be available. This happens where this happens in alpha beta grain bound phase boundaries. If there is alpha here beta here, so along this all boundary there will be equilibrium of alpha and beta, both phases is available and we call it at that boundary G is same. This is liquid and solid, both are same. This happens in the solid liquid, both are in available in both phases. That is in this phase, in this area within this solidus and liquidus line, both liquid solid is available, means both has the same energy. That is they are in equilibrium. The moment solid will have lower energy, please remember, the moment solid phase will have lower energy than liquid phase, That means free energy of solid is lower than liquid phase. All the liquids will start transforming to solid. Why? Because everybody wants to minimize their energy. In this universe, everybody wants to minimize their energy. Even if you have very tired, if you have done a lot of hard work, you have strained all your organs, okay, all your body muscles you have strained, so you have stored a lot of energy in your muscles, okay, then you want to minimize it. Naturally, it's a spontaneous process that you'll get tired and you sleep. Why? Because your muscles wants to minimize your energy. In the same way, so muscles like to be at lower energies. Not muscles, everybody in this universe, right? Similarly, if there is a liquid and solid together, staying together, okay, the moment you give the favorable condition, like you lower the temperature or you do something where you change the condition, and where you see in that condition solid is having lower energy than the liquid. This is a nature. This is a nature. If whether at particular condition a particular material will be at lower state or higher state, that is a nature of that material, okay, that comes with the atomic bonding and the arrangement where they can minimize their energy. So I'm assuming that I'm creating a condition where solid will have lower energy than the liquid. That's a typical condition called lower temperature. At low temperature, solid will have lower energy than liquid. So every liquid wants to become solid, so they will start transforming towards a solid. Okay, so when this solid will be stable than the liquid, where there is a solid has, in all region where solid has lower energy than liquid, in that conditions, in that region in your phase diagram, solid will be stable than the liquid. This is the only concept that you need to understand. That's it. Not at all anything else. Okay, so that means anything alpha, beta, gamma. If you are going in phase diagram, if you want to see with which phase will be stable or present in particular area, let's say in this area, which phase will be available. Okay, let me draw a typical diagram. Okay, let's say this. No, let me not write alpha. I'm telling you, fundamentally, if you plot G versus T curve for, let's say, क्या copper zinc, सही है ना? हाँ, copper zinc. So PBSN, let's say, it's a more popular example, iterative example, PBSN. Okay, so in PBSN, I'll tell you, I'm giving a system. Okay, so let's say it's a 99% PB and 1% SN, and I'm telling you, key draw GT curve. Draw GT curve. So in that GT curve, okay, mostly you have a alpha phase diagram. Then you are getting alpha plus liquid. There is a diagram for liquid as well, right? Simple, huh? Now this is the temperature where, see, I have drawn this diagram. Whether it is correct or not, I don't know. I'm just giving you a concept. Okay, you have to refer the book. Just I'm giving you a concepts. Okay, please understand. So this is a temperature where, let's say this is a liquid. Of course this is correct. This is a liquid and this is the let me check whether it's correct or not. This is liquid and this is a, let's say, alpha phase. At this, beyond this temperature, see, everywhere this liquid is having lower G value as compared to this alpha. Actually I should have drawn with the iron only, because we have alpha, gamma, and delta curve. So okay, let's see. So what I'm trying to tell here is, in certain temperature, the particular phase will have lower G value, from GT curve. Okay, and from that we know by nature, okay, by nature, which phase will have lower G at which temperature. That is known. That is by nature of that material. Okay, now if you know that, it's very easy for you to find out the GX curve. Okay, so by knowing the GT curve, you can know the GX curve. Okay, now, so our idea is G particular phase should be lower than GL, so that this become the stable. Okay, that's it. Now let's go there. I'm giving one temperature, this temperature. Let's say this temperature Tx. At Tx, tell me, in across all the, I'm drawing GX curve. Okay, guys, X here and my G here. Across all the X values, everywhere, whether at this X value, you see it is in liquid phase. At this value, it is in liquid phase, because this whole area is liquid, right? So in this composition, this is liquid phase. At this, it is liquid. So in all the composition range, my phase is only liquid. What does that mean? That means everywhere in all composition range at particular fixed temperature, let's say Tx temperature, my curve of liquid is always lower than curve of solid. How? I mean, then you can ask, sir, why are you writing like this shape? Why are you writing this or this or this? See, I have memorized certain things. Okay, this is a nature how these curves are found when in the experiment. Okay, so don't tell me you have to memorize few things. Huh? So this is the example only you need to memorize. That's it. Only four temperature. One temperature is this. One temperature is this, where it is touching slightly right side of the composition, and one temperature is this when it's touching slightly crossing slightly this left side of the composition, and one is the down. 1, 2, 3, 4. Only four different temperature. The nature of GX curve you need to understand, and that's it. You will be able to solve each question. Okay. So I have already taught it in the test series, but I'm repeating it because I'm going to upload it on YouTube. So please bear with me. I won't take much time. Okay. So I'm pretty clear. Okay. So across at this temperature, I'm giving you, let's say Tx, because T naught is already taken. Usually I take T naught. Okay. So Tx temperature, at this Tx temperature, okay, everywhere all composition, my L is stable in the phase diagram. It is already known. It is given, right? So in that case, means my liquid G value, this is my G and this is my X. X is my phase weight percent or mole percent, okay, fraction. I mean the what do you call it, composition, okay. So across all the composition, my this is my liquid curve. I can write, so I can denote it by GL curve. So my GL is always lower than the G solid, and that is why everywhere my liquid is stable. Now let's go to a temperature where it is crossing this liquid solid phase area region at slightly right side of the composition. Means it is slightly higher temperature, as simple as that. Okay. In that case, tell me, across this, across, you start walking with me. Okay, start walking with me. Start walking. This is the X, this is the 0, and this is the 100. Start walking with me. Right now it is liquid, 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 liquid till this way. That means this much, let's say this is composition, let's say this is, let's say 70%, right? So up to this much it is only liquid, means up to 70% the liquid is lower. This is liquid phase graph, and solid is higher, right? Up to, sorry, up to 70%, right? That is why you see everywhere liquid in the, everywhere liquid in the phase diagram. This is everywhere liquid, no? Let me remove and then tell. This is liquid, no? This all region is liquid. I took this temperature. Okay. Now see here. Now what happens is you have a both liquid and solid. Forget about this. Right now, this region. Now focus only this right hand side region. Let's say this is only 20%. No, not only 80%. Okay. So in this region, what is there? Only solid is there. Now you can say, sir, kaha solid? Where is solid? Tell me, no. So solid is, this whole region is solid, right? So this is also solid. I hope you understand this much, okay? So this part of your temperature line, this part is only solid. That means up from this 80 to 100, which one is lower? Solid curve is lower. That means this is solid curve. This is solid curve. Okay, that's it. In between there will be mix of liquid and solid. So how to draw this actually? So to draw this, you need to understand this. This will go slightly, and in this range, if this is solid, then where is the liquid? Liquid will be slightly up. Where this is my 80%, right? This is my liquid and this is my solid, right? Just like left hand side, right hand side is also same. Now comes the mixture of both liquid and solid. In that reason, you have to draw something like this. This solid will go and connect solid, right? And this liquid will go and connect. Okay, let me draw. Let me first draw and then explain. It's not difficult. Okay, so all the lines where two phases involved, it will form something like this. Oh, sorry, blunder. What is happening with me? It is given in here only. Okay, this is what I'm trying to draw. Huh? Or sorry, I cannot even move. It's okay. Okay, so I want to make something like this. So something like this. Something like this. As simple as that. Okay. So across this region, all my liquid is lower. Then across this region, now you find out the tangent. You find the tangent. And there will be a mix. Okay. So across this region, you get everything is liquid. Everything is liquid. Across this region, everything is solid. Everything is solid. And in between, you get a liquid plus solid. Okay, that is the idea. So you get first graph in 100% solid, and 100% liquid region. Then you get intermediate. You get the and now there is a two type of graph that can be formed. One is where my mixture zone is slightly right, and another graph where my mixture means both solid liquid is slightly low. I have a one graph where my mixture is slightly right hand side, means at higher percentage, and I have another graph where my mixture is slightly lower percentage, right? So that means I can make another graph where this part will be slightly this side, means something like this. Sorry about that. I mean, I want to shift this slightly to the left hand side, this curve. So that means this curve will be slightly this and then go like this, right? So you have something like slightly left side of this tangent. Okay, so that's what I'm trying to tell. Now, since both graph is given, now you understand it. Now tell me how difficult it was to solve. Okay, tell me. I have this, means two phase region. So there is up to certain range my liquid is stable. So up to certain range my liquid is stable, right? Means I have to draw the tangent. Sorry about that. I have to draw the tangent. So if I find this is where 100% liquid is stable, and of course my liquid is also stable. Now I'm traveling across the composition, guys. Okay, I've reached this place. I've reached this place. Now from this percentage to this percentage, I have a both liquid solids. Also, I have a both liquid and solids from this percent to this percent, right? After that, I get 100% solid. I get 100% solid here also. After that, I'm getting the 100% solid. Why I'm getting 100% solid? How did I know? Because my curve, solidus curve is lower as compared to my solidus curve is lower as compared to, see, this solid is lower. G value of solid is lower than this liquid, right? That is why this. So that is why it's very easy to understand. Okay, and the same thing is I've taught. Now, why this is not correct? Why this option is not? It seems also similar, but see, where is my? This is my. If I draw the tangent, this is my solid plus liquid, right? Right. This is my 100% solid. This is my 100% liquid, right? Right. So up to this composition, solid curve is lower than the liquid curve, right? So that means this is the composition where only solid is stable. Now you go and see from the array. यार क्या करूं मैं? Okay, so let me zoom it out. अरे यार ठीक है ना, इधर देखो ना. So initially which composition is stable at lower composition? Which composition is stable? Anyone? Liquid. So lower composition liquid, but in that graph solid was there. See, right? In that graph solid was there. That is wrong, no? Right? It was very, in this curve you see it's very easy. It's saying across all the composition range at that particular temperature, across all the composition, solid is stable. Is that correct? you have to see where your temperature line. Your temperature line is not here. That you're saying that across all the composition only solid is there. That is not true, right? You have both, so it is not possible. Okay, so I hope you all understood how to find out the from the phase diagram how to find out the gx curve, or from the gx diagram how to find out the phase diagram. Okay, so this is what, this is not true, and this is also not true. What does this signifies? Which temperature it signifies? Any one of you, can you please tell which temperature it signifies? It's saying across all the composition range, liquid is stable, not the solid in the phase diagram. Only at 100%, let's say B, percentage of B, let's say 100% of B, both solid and liquid is same. Means free energy of liquid and free energy of solid is same at the 100% of the composition. Both, otherwise everywhere across all the temperature, across all the temperature, across all the X at particular temperature, across all the X, my everywhere I have a liquid, everywhere I have a liquid, but at 100% I got a liquid solid both. Which temperature is that? Okay, just check from the phase diagram and tell. See, it's saying across all the composition, my solid is there, but at 100%, I have a both solid and both liquid and solid.
Solid.
So what is that temperature called? That temperature is this. Yes or no? This is the temperature, right? Yeah. No. I'm really sorry. This is not temperature, because across all the composition, your liquid is stable. Huh? But I need to give you the solid, very solid. I mean that this is the temperature. How is that possible? Across all the composition, solid is possible. Only this temperature, this composition, your both liquid and solid is there. So this is not possible because it was given at right hand side. No, let me see. Actually, that graph is wrong. Maybe. Means at 100% you get both liquid and solid, where all sahi to hai. Across all the composition your liquid is stable, only at this point both solid liquid is there. So that is there, no, at top temperature. Across all the temperature your liquid is stable. Okay, only this is the temperature where both solid and liquid is there, right? That means for this temperature that graph is true. For this temperature, what will be the graph? The graph will be something like this. They will meet here, right? They will meet here. This across all the composition, your solid is stable. So this curve is solid line, and across all the means lower than the stable means lower. G is lower, okay, and then it meets at here. So it meets here. I hope you understand. So there are 4 scenario. One scenario is this, where let's say liquid is always lower than solid curve, G solid. Okay, then you get this, where everywhere solid is stable. So everywhere, this is your GS line, everywhere solid is lower. Then you got this line where they will meet here, because this is where both solid and liquid is available. So they will meet here. G will be same here because they will be in equilibrium, right? They will be in equilibrium, means G of S will be low equal, then G of S will be similar to G of L here. That means your graph will be something like this. Something like this. They will meet here, right? Everywhere your liquid is stable, right? Everywhere your liquid is stable. Everywhere your liquid is stable, right? Everywhere your liquid is stable. Now you get another this temperature. I'll go in intermediate, that is there. There is another temperature where they are meeting at both liquid solids available here, liquid and solid available here. That means this is the point where GS and GL will become same. That is a congruent melting point. We call it congruent melting or congruent melting point of this A. That's a melting point. A congruent means where the transformation is happening at equilibria, or where G, S and GL both is same, okay? Or 100% composition is something that we get in the congruent melting point. 100% solid, 100% pure A or pure B can show you the congruent melting point. Okay, now so that means this point will show you graph like this. They will meet here, right? Very simple. Now any graph that will be any graph that will be any temperature that will have both liquid and solid, right? Any graph that will have both liquid and solid, they will have this kind of nature. Are क्या कर रहा हूं मैं? They will be something like this. Okay, they will cross. There will be a tangent. Okay, the tangent will decide this, where both phase will be available. Here it is pure liquid, here it is pure solid. It can shift towards right, shift towards left. देखना पड़ेगा कि किधर, where is your this mixture point. What I'm trying to tell here, see, what I'm trying to tell here is same thing. You can plot here as small, right? That means your solid and liquid both phases are available at 80 to, let's say, 90 to 95%. How you can find out this? For that, you have to plot very sincerely so that this comes at right hand side. It's intuitive. I hope you understand what I'm trying to tell. Something like this, right? Very right hand side, so that so that you can find out the mixture wala, so that you can find out the tangent here. Okay, so that this becomes even I am not able to draw, but it will be shifted. This will be shifted towards right, because you want to find the mixture right. You can find the same thing towards the slightly left, like this. Okay, if you plot something like that. Okay, so it's a structure of geometry, but I hope you understood this. Okay, it's very easy. Okay, now next question. So if someone who has already just read my slides that I've given in the test series, okay, forget about my regular batches. If you join my regular batch, you can find all these concepts. They are the simple concept that we explain at the first point, then we go in the deeper. Okay, so if you would have just read, I hope every one of you have already read it. Okay, the slides that I have given, at least see the graph. Okay, how they are changing. They can simply ask the graph as well. Okay, the slides that I've already shared you all. What is the slide? That slide is Professor Ajit sir's notes in the electronic properties of material. Okay, I have already shared this. Okay, this lecture certain lecture number. Okay, uh, I hope I've already shared this notes to you all in the test series particular drive folder. So you go and see. Okay, so in this, if you see all this, they are discussing about the, what is that, silicon. Okay, silicon or intrinsic semiconductor, and they are saying how IBM has already developed the silicon wafer. And after that, this is all notes from Professor IT Bombay's Professor Ajit sir. Okay, so I'm gonna give him the credit, but the sole purpose is to teach here. So you see, this is all about the typical silicon. What you see, silicon matrix. Okay, where the energy is getting absorbed and the electron is getting transferred from valence to conduction, and you get this typically transformation and electron transition. Okay, this is typically the silicon. Okay, valence conduction band, how they are connected with each other. Now this is typical valence band conduction band, how the electron is jumping, how this electron hole annihilation or splitting is happening. This is typically the band diagram. Okay, hole energy, electron energy, all this. And this is v equals to nu e, that we all know, the mobility and drift. See here, this is the graph. Okay, if you have just seen this graph, you can answer that question so easily. It's saying the same thing, how density of states. So we have already given a lot of time to teach you density of states. Okay, how to calculate density of states in 1D, in 2D, in 3D. This question is also asked in gate. Okay, and how the calculation is done, but understanding is very simple. How GE changes with E, whether to the half power or whether it is constant. So it depends on, for 1D, 2D, 3D, it changes. For 3D, of course, we're talking about 3D. You see how this energy and G of E, how G of E is changing with the energy. That is where you're getting the band. Okay, so the band, if you see here, the band that you're seeing here, how the density of states, how density of states is distributed across the band. What is density of states? DE. Density of states is the number of states per unit energy. Per unit energy. How many is the number of states? So dN by dE. Number of states per unit energy. What is state? What is state? State is the, what is the state in SPDF electronic configuration? What is state? Anyone? What is state in electronic?
Number of electrons.
Sorry,
Number of electrons.
What is energy state in electronic configuration? Like I'm writing 1s2, 2s2, 2p6. Okay, so if you draw the electronic configuration, this is the 1s2, this is the 2s2, right? And this this is the one first cell K, and this 2 is the L, right? Right. So in first you have only S orbital. In the second L, you have a S and P both orbital, right? S and P both orbital. So each orbital, okay, each orbital will have a energy state. Each orbital will be occupied with two electrons with different spin. So that orbital will be stated at particular energy. If this is E axis, if this is E axis, okay. So this orbital represents the energy state, EI value. Okay, समझे? So orbital has certain energy, so electron will occupy that orbital. That means that electron will have same energy state. Okay, so how many orbitals are there where electron can occupy is the energy state. Okay, you understand? Number of orbitals, that is where electron can go and sit. Okay, I hope you understand. So this whole orbital is not one state. One orbital has two state. One orbital has two state, right? One state is having the quantum numbers, right? And then all quantum numbers same, both state will have the same quantum number, only the spin quantum number is different. This is for plus half and this is for minus half, right? All other quantum number will be same. So each electron with a completely distinguished quantum number will have a state. So each electron, it takes a state at particular energy level. We call it energy state. Okay, I hope you understand. I hope you understand. So this P6, P has three orbitals. Okay, that means six energy states, and each state is taken by electron. So number of state is number of electron. Okay, at particular. So this is particular three. I mean, each state has the same energy. See, all this electron is the same orbital, right? So energy is same. If you plot energy versus orbital graph, okay, it's the same. But the state, quantum state that each electron is taken, so this all electron is having the same quantum states, okay, and energy is same. So that means a particular orbital is staying at particular energy is going to give you the particular energy state where certain electron can go and sit. Okay, I hope you understand what is energy state. Energy state is the space where the orbital where electron can go and sit. So you see here you have a lowest energy density of states, means number of states per unit energy. Lowest density means here there will be there is not much orbitals where electron can go and sit. The maximum number of energy states available to fill occupy by electron, maximum number of DOS means maximum number of N. What is N? Number of electrons per unit volume, right? Number of electrons. So I have already given you the formula, no, how to calculate the number of electrons per unit volume. If you have not learned this for 1D, 2D, 3D, okay, please watch my previous year solution. So and also I have done a mistake while adopting the formula for 1D. So I've already given in the comment in description what is the correct formula, but the concept is same. Okay, how to calculate number of electrons for 1D, 2D, 3D if you know the DOS. Higher the DOS, more the density of state, more is the density of state, more is the orbital, more is the orbital means more is the electron. Simple. Okay, so that's why integration of G of E with the probability. What is the probability? Fermi-Dirac function. If you integrate this, you got a number of electron N. Very simple. Okay, I've already given you. So more the density of state, more is the number of electron. So what I'm trying to clear is that this is the place where you have a maximum number of density of states. Okay. So if you increase the energy, this is where maximum density of states, and then you keep decreasing. Okay. Then there will be no density of states here. Means there is no states to even sit. That is why we call it what do we call it? Gap, band gap. There is not a single orbital where electron can sit. Okay, electron can occupy because there is no density of states. There is no density of states. There is no states. There is no orbital. Okay, that's why you see there is nothing here. We call it a gap, and then you start getting states. It will keep increasing up to certain, and then it will start decreasing. Okay, so this is a typical nature of the GE versus E diagram, and this is the actual, and this that we draw is a simplistic version. So in terms of probability, we draw like this. Okay, and in terms of GE, we draw like this. Okay, I hope you all understood. Okay, so it's a simple, if you simply, so please, you don't need to solve and see all these equations. It's not necessary. Of course, some equations are important to solve numericals, but at least graph you should see. Okay, that is enough for your gate question. Okay, so of course, which one is the correct? C is correct. Okay, now let's go to the next question, and this is something that I usually teach. And learning to find out Miller indices for planes is so interesting, so amazing. But never ever in the gate exam there was a question where a plane is drawn and simply Miller indices is asked. This type of question can only be asked by IIC Bangalore, because they give I have so much respect for them. They give space for even finding Miller indices, a question based on Miller indices. Can you imagine? I mean, you know the Miller indices, then you can solve XRD questions, you can solve PD, planar density, linear density, blah blah blah. There are many things. Okay, sleep planes and all. That is applications. But they were more interested to find out whether the student know how to find out planes, how to find out indices from plane or from indices to plane. Oh my god! So I was so happy to see this question. So if you understand, if you're not, and if you don't understand how to find out Miller indices from plane, or how to find out plane from Miller indices, please join my at least crash course. I will teach there. I'll give for 2 to 3 crash course or test series. If you can't afford the regular batch, I'll teach how to find out this. Okay, at this moment I cannot give the whole theory of Miller indices, but I'm gonna be very small. Okay, because it is available everywhere in YouTube. You can watch, or I can guide you. Okay, just you just reach me, you just have a text to me. I'll teach. Okay, so what is the idea is to find out first. Okay, so let me give you how to find out. Okay, so idea is to find out first what is my origin, then what is my axis. If you find out that, then you find out what is my intercept. Okay, what is my intercept, and to find out intercept, then what is my intercept on x, intercept on y, and intercept of z. Once I know my intercept on x, y, and z, okay, then find out, this is my intercept. I'll tell what is this ABC. And if I know, then I have to reverse it. Okay, means reciprocal. And then I have to simplify by multiplying with LCM of all denominator. This is a standard procedure that, and then I can put in the parenthesis. Simple. So this is the stepwise step. Okay, you have to find out the step. Okay, otherwise it is just wrong. So this is a reciprocal. Sometimes you take shortcut and you make mistake. Okay, this is intercept. Simple. Let's find out now. So what is my origin? So origin is decided where your plane should not pass through the origin. That is the only criteria. And you find out according to your convenience, so that you know the intercept. So this is my origin. If I'm assuming here, then I know I can take any x. If I'm taking this x, then this will be my y and this will be my z. Remember, how I'm choosing my axis will depend on this anti-clockwise convention. Please follow anti-clockwise. I mean, you cannot write this as x, this as y, and this is z. This means you're coming to the clockwise. That is wrong. Okay, you always choose anti-clockwise. It doesn't matter from where you start. You are starting here, you can start from here. This is x, this is y, and this is z. That's also correct. You can start from here as well. This is x, this is y, and this is z. You can, but you have to follow the anti-clockwise. Okay, you can start here. So I usually start from here. This is my like. Okay, liking, disliking, simple. So I start from here. This is my x. Sometimes people also write z, but that's okay. This is x, this is y, and this is z or z. Okay, now I found out my origin. Because of this origin only, I know where my this plane is cutting to my axis, right? I know where, and this is the simplest plane as well. This is not parallel or something confusing. It's very simple. You know, this is the intercept, this is the intercept, right? So this my origin is correct. Next, find out the intercept on the axis. Find out the axis. I found the axis. Now find out the intercept. I found the intercept. On B, it's cutting B by 2. On C, it's cutting C by 3. On A, it's cutting complete A, right? So my intercept is going to be X. X how much? B by 2. Sorry, X is how much? Complete A. So my X is A. Okay. So A by A. And then my Y is half of B. That means Y is B by 2. Of course, B is already there in the expression. And my C is, Z is, how much is Z? Z is C by 3. So my Z is C by 3 by C. Okay. So some people directly write. How they write the intercept? They write this as completely just 1. Actually, it is 1 only. A by A, it's a 1. And they simply decide directly write as half. You can write half if you have understanding, but I'm writing this. So B is going to cancel out. It's a half. Okay. And then this they can write a 1/3. Okay. They can write 1/3 because it is 1/3 of total. But actually, you can solve this also. Okay. You can solve this also. C is cancelled out. It's a 1/3, right? So you got an intercept. Okay. Now you take the reciprocal. Now you take the reciprocal, reverse of it. It's a 1, it's a 2, and it's a 3. It's a 1, 2, and 3. Now you don't need to take the LCM and multiply with LCM to make the smallest because they are already in the simpler form. 1, 2, 3. If I'm not wrong. Yes, I'm correct. Imagine karo this intercept is very awkward, like 1, 2 by 3, and 1 by 3. Now, the moment you get the reciprocal, it becomes 1, 3 by 2, and 3. Now you got a fraction. Like this, you got simply the integers. You got a fraction. You have to convert into integer. So you have to take the LCM of all the denominator. Here denominator is 1. Here it is 2. Here it is 1. What is the denominator LCM? 1 to 1. It's a 2. So you multiply everywhere 2, right? So here multiply by 2. Here multiplied by 2. Here multiplied by 2. So this becomes 6. This becomes 2 is cancelled out, right? This 2 is cancelled out. So it becomes 3. And this becomes 2, right? So your answer is 2. So here you have to multiply. But somehow, fortunately, we got directly integer. You don't need to do this step. So your answer is 1, 2, 3. Okay. I hope you all understand. Please repeat it. You watch it once again. Okay. You'll get your answer. It's very simple. Okay. If you have still got a lot of issue with this, please reach me. Okay. My number is in the description. You can join the Telegram channel and you reach me. Okay. I'll help you out. My ultimate goal is to help each and every one of you, right? Irrespective of whether you join my class or not. Okay. I'll be happy to help you. Okay. So don't think like you have to join the class. Even though students learned at 50%, 100%, that's a different thing. Okay. Now, or you join just the test series. Okay. Now, next question is 56. Next question tells you about the the same question. Oh my God, this question is a Fermi Dirac function question that I have taught you all in test series as well as a regular batch, right? Fermi Dirac function, how Fermi Dirac function is changing with E. Now you think, sir, what is this Seebeck effect? It's nothing. It's a Fermi Dirac function only, which is telling the probability of occupancy at particular states where EF is Fermi energy that we have already learned, right? Fermi Dirac function changes like this, where this is your 50% half probability. This is your 100% probability. This is your energy, right? And this is happening at any temperature T. Let's say if you are doing the experiment at temperature, so if you're doing the experiment at T equals to 0 Kelvin, then this graph will become like this. This graph becomes like this, right? This graph becomes like this, right? Means this is at 0 Kelvin, and this curved graph is at any temperature T. Now my question is, can you not just rotate it and find out? It's so easy, right? So what does it saying? It's saying ki I have rotated this, where I have written this. Of course, this is your Fermi Dirac function f of e, where it's half at here, it's 1 at here, and it changes. Okay, from 0 to 1. F of e changes from 0 to 1 because it's a probability. Probability is always 0 to 1. Okay, if you rotate this, you'll find this answer. What is this answer telling you? It's telling you, okay, if you rotate this, it's rotate this. क्या कह रहा है? What is this? 50% probability at EF. 50% probability. Let me change color. 50% probability. Which color I should choose? Green is okay. 50% probability at EF. Right? Now this is also confusing. Okay, so you have to figure it out. Huh? Let me find out. Now one probability is one, and then becomes half at increasing energy. If I keep increasing energy, probability keep decreasing and becomes zero. Same is true. If I increasing the energy, probability is one decreasing to half and then zero. This is not true here. Why? If I keep increasing energy, my probability is increasing to one. That is not true, na? If I keep increasing energy, everything is true. See, point half, 0.5 half, but it's very confusing. But you can think of it. If you keep increasing the energy, if you keep increasing the energy, let me hmm. if I keep increasing the energy, what is happening? My probability is initially one, and then it's becoming half and then zero. If I keep increasing energy, my probability is one, it's becoming half and then zero, right? Here what's happening? Here what's happening? If I keep increasing energy upward, going upward, my probability is becoming greater than one. That is not true, right? So this is the answer. Why actually this graph is plotted? So you might have said, sir, I know Fermi Dirac distribution. Okay, I know F of E formula as well. Okay, but the problem is there was Seebeck written. Actually, this graph is for T equals to 0 or T equals to any temperature, 10 degree, 20 degree, 30 degree. How exactly you find out? Okay, what is the probability that you will find 100% electron in your topmost energy level? You found out from the heating your rod, and if you heat the rod, your electron will move from higher temperature to the lower temperature T1 to, if T1 is higher than T2, then your all electron will start flowing from higher temperature. Let's say this is 100 degrees Celsius, this is 5 degrees Celsius. Okay, 5 degrees Celsius. Then all the electron will start moving towards this. Okay, so if this rod is hot, this rod will become also hot with time. Why is this happening? Because electrons start moving, and that means we get a current. We develop a voltage. That is what we call it a Seebeck effect. Okay, so this is happening. Why? Because here all the atoms are there, all the atoms are there. Each atom is having a energy, right? K, L, M, N, right? This is the energy. A cell, each atom is having nucleus, then cell, each outermost cell have a orbital. That orbital has to be filled, right? So when the electron start moving from this direction, okay, with carrying the certain energy h nu or heat, okay, they will start transferring that energy. Why? That electron will start filling the outermost shell of these atoms at this side, and then there is a probability calculation that you can do, and this graph you can plot. Okay, so idea is, so that IC Bangalore people or professors are so genius, they converted that Fermi Dirac function concept towards a real example of hitting a metal rod. Oh my god, can you imagine? So that kind of understanding they have. Okay, so they just don't understand, don't memorize this graph, f of e versus e versus f of e. Okay, but they know actual application in Seebeck effect. Okay, so that's a very interesting thing. And next is the what is the LED? I mean, in typical LED, what is the typical type of material used? So actually they are talking about LED application of optical properties. One application is LED, another is laser. Okay, and then we have different diodes. So optical properties application is LED. Okay, so the semiconductor materials are used in LED, whether they are direct or indirect. Indirect with certain impurity, indirect with certain impurity, or indirect with no impurity or transition metal impurity. What is happening here? Okay, so let's go quickly and I'll show you the all concepts behind all properties, all applications, and all impurities. Okay, so that you don't need to read it again, and this concept you can carry and give your exam. Okay, so just give me a second. Let me open my PPT. Okay, so forget about this answer. Okay, you will reach to the answer once you understand all every things that is given in this question. What is LED? What is indirect band gap? What is direct band gap? What is isoelectric impurity? What is their implication, application, effect? Okay, and the varieties, examples. What is this typical transition metals? And okay, so we'll go very quickly in very condensed manner, okay, so that it won't take much time. Okay, so because this video is already too long, I think I have to upload it in more than one part, but that's okay. Okay, you guys had to learn it very quickly, so very efficiently. So direct and indirect band semiconductor, this is a typical diagram that you have to remember at any cost. Okay, so this is the diagram that I have given you once again, whether I've already given this in gate test series as well, but this, see, so what is the band? We know like this, okay, but actually in DOS form, they are like this, and in probability of occupancy they are like this, okay, means in sorry, in k vector space, means momentum space, they are like this, okay. So so here this is momentum, that is h cross k. So we plot, so we can also write k vector here. This axis is k value, okay, or momentum. This is energy. If you plot, so here, if my electron wants to jump here, it will become hole, and here it becomes electrons, okay. So it's a simple, in your crystal of semiconductor, one atom is there, one atom is there, there. So electron can go from outermost cell of this, that is a valence cell. From the valence cell, electron can simply go and occupy the another what do you call it, energy state, where it is free, whether it is free, and it can roam around the crystal. That is what we call it, material becomes a conductive, right? Now, so if this electron moves to go in a conduction state or free state, it has to collide with other electrons, other positive ionic cores, which each electron, if it will remove, the atom will become positively charged, right? It's simple concept. So cores, okay, collide. So there is a movement of electron, okay, momentum. That means phonon is involved. What is phonon? Phonon is the vibration. Okay, if electron will collide with the other positive ionic cores and other electrons, okay, so if that means an electron carrying certain energy will start move. That means the energy will contain its corresponding vibrational energy, right? If you heat any atom, like rod example you take, if you heat that rod, each atom will start vibrating, right, with kT energy, and vibrating at kT energy, and an electron will start coming out, start jumping from the band gap, and they are coming to the conduction, they are start moving. If you heat it, right, if you apply the energy, HNU energy, now that means your atoms are vibrating. That means if your atoms are vibrating, there is a phonon created, the lattice vibration created, okay. So that vibration is phonon. That phonon can interact with this electron, the energy that you have provided to your crystal. Let's say you're heating it, like increasing the temperature, so your intrinsic semiconductor will become more conductive. Why? Because with the temperature, your conductivity will start increasing. Why is that happening? Because of the energy will electron will easily jump to the conduction, it will jump this gap, okay. It's a simple concept. Now but there is a vibration as well. Vibration is phonon as well. That phonon will start colliding with electron, that is it. But what is interesting in this momentum where the phonon is involved, an energy diagram, if this band is up direct, means this space to occupy in conduction is exactly same without changing momentum, without going in x direction, that means k vector without changing. That means it's a direct, okay. There is not a k involved, momentum involved, there is not k, there is not phonon involved. You don't need to need phonon to go to occupy certain valence cell, right, conduction cell, so conduction energy state. So here you see, if you go, you have to go right or left, right. That means you need to collide with the vibrational energy or vibration or phonon, and then after collision you will go, so you start changing your momentum as well, a k value as well, and that is why this is indirect. What is happening is, the moment you apply the energy hnu, if it is directly going to the conduction band, and then it is directly coming to the coming back to the valence, it will emit the energy, the photons, and then photons will have hnu energy. This hnu is hc by lambda. That lambda, if it is in visible range, you get a emission of light. because that lambda is in the visible range. Visible means from blue to red. Okay, so visible range from the 300 to 700 up to. So that means you get a light emission from the material. This is the concept we use in LEDs, where there is a visible light emission. Okay, so what we are doing, we are providing the energy in terms of voltage or current. In LED, we are providing the energy h nu in terms of voltage current. That energy is exciting the electron to the conduction band. Once they are excited, they will always come back because everybody wants to minimize their energy, right? The fundamental law of thermodynamics, right? Everybody in this universe wants to minimize their energy. Okay, so how they will minimize their energy? By coming back. So they will come back to the lower energy state, right? And then they will emit the h nu energy. If so we need a semiconductor which has exactly that Eg, so that that is, let's say let's say 1.1 for silicon. Okay, of course, silicon is indirect band semiconductor, we don't use that. Let's say gallium arsenide. Gallium arsenide has a particular Eg value, such a what do you call it, tuned Eg value, so that we get lambda exactly in the 300 to 700 region, so that we get a light. Okay, what is happening in indirect semiconductor is, it is start colliding with the phonons, it is start losing the energy. If it will start losing the energy, that means we won't be able to get the same lambda or h nu. If we won't be able to get same because energy is lost in the phonon interaction, so won't be able to get the same lambda, and also the emission efficiency will be lower. That is a common sense that one have to, because more path traveled, more energy loss. Okay, now let's go to the indirect band semiconductors examples. Okay, so it's very important to understand, know the examples and their applications. Okay, so as all the elemental like silicon, germanium, they are indirect band semiconductor with this band gap. It doesn't mean they will not be able to use. We use silicon, all the transistors, all the chips, all the vapor, silicon is used, right? So all the electronics, whole electronics industry is based on, what do you call it, silicon, right? Silicon, without silicon, germanium, whole semiconductor industry is nothing, right? So microelectronics, IC circuits, and solar cells for energy conversion. For energy conversion, it's okay, but for emitting the light, visible light, is difficult. Okay, silicon carbide for the high power electronics where high temperature is there. If temperature is there, silicon cannot be used. Why? Because silicon has temperature dependability, right? It has lower thermal stability. Silicon carbide can withstand high temperature. That's why they can be used for the power electronics and other some specific condition LED. But forget this LED. Okay, because one more thing I want to tell. This zinc phosphide, okay, or in some case tin selenide, they can behave like direct as well. So some semiconductor has both components in their band gap diagram, both direct as well as indirect, in very because it depends on the composition of zinc and phosphorus. It depends on the composition of Sn and Se, right? So the more impurity you add, depending on that, they become band direct or indirect. But as a overall, if you want to memorize, these are the typical, you can say safely, the indirect, and this is their applications. Okay, the important thing is they are less efficient for light emission, as the reason is the energy losing because of the phononic interaction. Okay, so because of the lattice vibration, there it is an involvement of lattice vibration. Because of that, you get a less efficiency. Okay, electrical conductivity we can enhance by doping in these indirect band semiconductor using transition metal, or using the what do you call it, isoelectronic impurities. You can do that. And energy conversion application we can use, for example, in solar cells, solar panels, all this. Okay, so please memorize this, at least not memorize, at least know the examples. Okay, they can ask and they have asked. Okay, now direct band semiconductor. So all the typical semiconductors where third, fourth, or second, sixth are the combination. Third group of periodic table with fourth and second, sixth, all this. So gallium arsenide, indium, these are the all direct band semiconductor. You see, zinc phosphide is in the this also. Okay, so don't be confused. So just remember. Otherwise, but they are not used in. Usually, they all are used in LEDs, blue LEDs, green LEDs, all those LEDs, infrared detectors, and sometimes in quantum dots as well. So this is the example that you need to understand based on their efficiency. Now, So this is the keep high emission, high efficiency, and sometimes they can use in the laser and solar also. But the indirect cannot be. They can be used in solar, but they cannot be used in LEDs. Okay, just understand, because this direct can be tuned with wavelength. They can be doped with the transition metals and isoelectric electrons impurity. They can doped with the impurity, and then with the doping in impurity, what happens is, if there is a this if there is a conduction band and there is a okay, I'll come to that. Okay, I'll come to that, I'll explain the impurity. So this is the application. Okay, please memorize this. Now that question that is asked is LED. For LED, which one of them will be um, uh, correct? So to know the LED, need to know all the optical application that is important. Okay, so we have a typical phenomena, optical phenomena, we call it luminescence. These are all the optical phenomena that we get, okay, depending on the material and the structure and the what type of light that you're putting on it. So you get a luminescence phenomena in the optical materials. Laser is also one kind of phenomena. Thermal emissions, photoconductivity, optical fibers. These all are the phenomena. Based on each phenomena, there are few applications. For luminescence, you get a cathodoluminescence in the SEM, scanning electron microscopy, right? Transition electron microscopy. To bombard the electron, how we do? We use the cathodoluminescence effect, okay? Then we have photoluminescence that we use in solar cells, right? Then we have a electroluminescence that we use in LEDs. Okay, so we'll come to that. Okay, so laser is also there. Please read Callister book of optical properties. You will understand more than enough for this applications. We'll discuss luminescence because our gate question was on luminescence. Okay, means LED. So luminescence on typical conditions, okay, so it's a typical intensity varies with the T and tau. Please remember this equation, okay, you can ask. And this is a typical equation that we already use in Callister also, it's given, okay, in terms of refractivity and reflectivity. Okay, so depending on the energy source, what is your energy source, you can divide them depending on how much. Okay, so what is luminescence? Let me tell you. Okay, what is the definition of luminescence? Okay, so you have a semiconductor and you apply a energy or light or heat or let's say dhoop light. Okay, solar light means light from sun. Okay, if you apply that energy, there is a bands, and because of bands they will jump, the electron will jump to the higher energy conduction band, and they will come back and then they will emit energy. That is the overall. You input, then the transition, then output, and you get, if you're getting light or visibility, we call it luminescence. Means it chamak raha hai, right? It's showing luminescence. Okay, now, so how much time? So if the emission radiation occurs within 10 per minus 8 second of excitation, like you excited, right? You excited to the higher energy state or valence band. How much time of that excitation, like after excitation, it is taking less than 10 to the minus 8 seconds, very quickly. The moment you apply light, very quickly you start seeing the light coming out of the material. Okay, we call it fluorescence. Okay, the moment you put light, at the same moment and you remove the light, you start getting the light coming out from the material. Okay, chamakne lagega turant. That means it is showing the luminescence. But if you excite it, it is taking a lot of time. I mean, not a lot of, more than 10 per minus 8 second. It's there's a lag. If you give the light, you put the torch here, light here, and then you leave it, UV lamp here, and you leave it. Okay, for a bit later time, it will start showing the luminescence. That luminescence is called phosphorescence. So depending on the period or time or nature of the that luminescence, we call it fluorescence. But what is this energy source? Depending on the energy source, they can be divided into three major categories, and that I would like to take your attention. So if the emission nature, we all know 10 per minus 8 second, higher, lower than 10 per minus 8, that is a phosphorescence, then or a fluorescence, and then higher than phosphorescence. Energy source of the electron excitation. What is the energy source? You can divide it into photoluminescence, cathodoluminescence, and electroluminescence. Okay, so photoluminescence, by nature, photo, it is either lights coming from the sun. Okay, electroluminescence, by the nature, the energy that you put on your semiconductor, okay, is the voltage or current, electrical energy. We call it electroluminescence. and then there is called cathodoluminescence. You are using the cathode, okay, to get the cathode radiation you are getting to get the luminescence or the light coming out of my semiconductor, okay. So based on that we got a photoluminescence. So you typically know, right, this you have already seen. So we call it a fluorescent lamps, okay. So the where we use calcium halophosphate phosphor. This is a phosphor we use, okay. uh, Even fluorescent you can make the quantum dots, carbon quantum dots, okay. CQDs you can make, and you can make a solution. I have done this in my MTech, okay. And if you put, the moment you put under UV light, they will start but lighting like this. If you remove the UV light also, they will start looking like this. That means they are fluorescent, fluorescence they are showing, okay. So the photoluminescence occurs in fluorescent lamps, okay. So the energy source is, if energy source is fluorescent lamps, I mean, sorry, the fluorescent lamps are the applications where we get a photoluminescence. I'm really sorry, okay. And of course your energy source is light, okay. Energy source is light. The fluorescent is one application of this photoluminescence, okay, this typical fluorescence. Now cathodoluminescence, we get the applications are electron microscopy, like same cathode ray oscilloscope or cathode ray tube, that you know, color TV screens. They are the applications where the energy source is the high energy bombardment of the electrons, okay. So energized cathode, that is going to generate the high energy bombarding electrons. Energized cathode we use in the electron microscopy, that you know, from that tip, electron gun tip, okay, we are getting the electrons, right, coming in the electron microscopy. So that is a cathode tube, right. It is either lanthanum boride or LaB6 lab or tungsten also, right. They're the tip, they're the cathode, right. From there you're getting the electron generation. So you can get the Cl, cathodoluminescence, from the material. So there's a many kind of signals, secondary electron signals, backscatter electron signals, X-rays. Then you get a cathode Cl rays, okay. Cathodoluminescence you can get from the material, okay. But the energy source is cathode, okay. So this is the Cl that you know, that is typically observed in electron microscopy, or even TV screen also we are using the same. Now comes the LEDs. If your energy source is electrical energy, where you're applying the voltage and current you're applying, okay, forward bias voltage if you're applying across the device, okay, you are getting a lot of combination of electron and hole combination that will result into energy, okay. And that for that you must use indirect semiconductor, but you can use in sorry, direct semiconductor, I'm really sorry, direct semiconductor, or some impurities. We'll come to that, okay. So this is the typical direct semiconductor with different compositions: gallium nitride, gallium phosphide, gallium arsenide, gallium all those materials. And they have particular HNU, where HNU, they will emit the HNU from the transitions, okay. From the transitions they will emit the HNU. That HNU will correspond to SC by lambda, then the lambda corresponds to this value. If I want to get red LED, you have to use this semiconductor. If you want to get blue, so blue LED was very rare. Actually, blue color is rare in our nature, okay. Can you tell a single natural things available which is in blue color? It's very difficult, okay. You just try to find out everything okay. Don't forget about the synthetic blue colors or dyes. These days we invented blue colors, but during our freedom fighting, okay, freedom 1940, 1947, 1930, the blue colors were rare. So the Britishers used to force us to what do you call it, harvest blue dyes, okay. We call it neil, okay. So they wanted to make us dye so that they can sell that in European markets at very high cost, okay. So blue color were very, so the moment our scientist first in 2000, in the very few recently, he invented that blue color LED, and he got Nobel Prize by that. So getting blue color LED is very tough, okay, because the lambda that you need is very unnatural, okay. Because lambda, if you see in the spectrum of visible light, blue color is at the lowest wavelength. It's very difficult. All the semiconductor that we had could not give you the HNU which correspond to that lambda, blue color lambda, okay. But nowadays blue LED is invented and we have that, but before that it was a rarity. So you can use direct semiconductor to use the LEDs, means you can get particular lambda and wavelength, but you can use the impurities as well. Okay, so isoelectric impurities means those atoms, okay, those impurities which has exactly same valence electron as the host. What do you mean? So Kasi G SNPB, right? Kasi G SNPB, okay, bell guy in thalassi. So that means instead of gallium, you can put indium. Like if you have a gallium arsenide, you can dope indium in it. So it can replace the gallium. Now see, gallium has same valence electrons, third group, and indium has same valence electron. Almost their crystal structure is also same because they are in the same group. So they're all most of the properties are same, right? So because isoelectronic means same number of valence electrons they possess. Okay, so if you in gallium arsenide, if you it's a direct semiconductor. Okay, if you dope indium into it, so it will replace few gallium atoms in the crystal structure. It will the indium the all are gallium. Okay, and it will replace few gallium into indium. Okay, and because of that indium, what is happening, that is very important. The moment you so see, the doping that we do is the doping which has either lower valence electron or higher valence electron. If it is having higher valence electron, we call it n type doping. If it is lower valence electron, we call it p type doping. Like doping phosphorus, right? Doping phosphorus in silicon is n type doping because phosphorus has 5 valence electrons, silicon has 4 valence electrons. There is a net one extra electron. You can dope boron or aluminium into silicon, right? We call it p-type doping. Why? Because there is a shortage of electron, right? Similarly, you can dope exactly same number of valence electron. We call it isoelectronic impurity. What does it actually do? This phosphorus or doping aluminium is trivalent or pentavalent doping. It can change the charge. So you have to balance the charge as well. That means you are creating a lot of defects. Like if there will be charge imbalance, that charge imbalance will be stabilized either by interstitial impurity, right? The charge can go to the interstitial side. You can create vacancy as well. We have already learned in defect reactions, no, how this mixing can create defects. Frenkel or I mean interstitial as well as Schottky or vacancy. Okay, but this isoelectronic impurity will not create any defect, will not create any charge imbalance because they have the same charge, same valence electrons. Okay, they have same valency. Second thing, but how it's improving that? In this case, they have slightly lower electrons. That means they are creating holes. In this case, they have one extra electron. They're creating extra electrons. Okay, but how this indium is benefiting your gallium? Okay, how it's helping? So it's helping because it can generate. Okay, first of all, there are two type of let me give you the type. Okay, let me tell what exactly they do. So they can, so you have a valence electron here, sorry, valence band here, and you have a conduction band here, right? I am really sorry. You have a conduction band here and valence band here, right? Now they can generate a energy state intermediate, okay, to the existing energy state. We call it localized energy state within the band gap of the material. Okay, that is very important to understand because each material will have different energy state or DOS distribution. If you increase the energy, number of states will vary, right? Because each material is different. Each atom has different orbitals, right? Each orbital has different electron filling, right? So each atom is different. That's why their energy states distribution is different. They creates a extra trap in between valence and conduction band. Extra energy states they create, the impurity they create. Okay, what does do? It actually modified the whole band structure, and because of that, it can give you, it can either it can enhance the conductivity, it can enhance even this emission, it can modify the emission, means you can get the different light, different color, because you can get the different wavelength because you have, because it was eg this much energy, now it is only this much energy. Since you have changed the energy, that means you have changed the lambda. Okay, so you can modify the LEDs. Okay, so that is the function of isoelectronic and definition. Okay, now there are two type of isoelectronic impurities. One is called that they can be completely soluble with the host. Okay, so electronic impurities based on their solubility, so and the how much discrete energy levels they can create. So limited solubility, we call it first type of impurity, and if there is a complete solubility, we call it a second kind of impurity. Now example of first kind is the gallium phosphide, where I am doping nitrogen to replace phosphorus. Why? Nepal, Pakistan, Australia, sub, whatever you say. So in gallium nitride, I can remove the nitrogen, I can dope with phosphorus. I'm really sorry. In gallium, same is true. In gallium phosphide, I can remove the phosphorus in the host atom, it can be replaced with the nitrogen, okay, in the host, and then that nitrogen will create a extra energy low levels in the edge of the valence band. Okay, near edge of the valence band, that means you're modifying the overall electronic transition, means energy, means h nu, means lambda, means color of the emission. Okay, I hope. And also doping will give the conductivity as well, because sigma equals to ne mu. If you're changing the mobility by putting the dopant, of course you will get the conductivity. Sometime you can make the magnetic superconductor by modifying the spin of the electrons. This spin of the electron, because each element will have different atom, each atom will have different energy orbital, each orbital will have different electronic quantum states, means spin. Because of this spin, we can use this spin to store the information. Okay, just like we are using the bits to store the information in computer memory, we can store the memory or information in the spin as well. This branch of science is called spintronics, and this is the latest and very current trending branch of semiconductor, and trending what do you call it, technology topic at this time, where all computer will become quantum computers, where they can calculate billions of the information. I mean, they can analyze data of all the date of birth of all 7 billion people within 1 second. Okay, so the quantum computer will use spintronics as a, where your spin will store the information. This is so spin is so unstable or so fast or so quick. Okay, they can use this spin to transfer the information from one atom to another atom, or to in the electric circuit. Okay, so that's the idea. So you can dope to get the, what do you call it, spintronics as well. That you can do in the transition metal impurity as well. Okay, we'll come to that. So this is what you just read it. It's a simple idea. You know the examples. The gallium phosphide, where you're doping nitrogen. The CDS, where you're doping the telluride. Only condition is one of them should be in the same group of the dopant. Like CDS, what is this? Osama Saudi say, right? Osama Saudi say tempo. So you see, your tellurium is in the same group of sulfur. So that is why you can dope the tellurium to modify the band structure. Okay, this is the only idea. They are widely used in development of LED and laser. Why? Because you can modify the emission. Okay. Now let's go to the second transition metal impurity. So this transition metal impurity can be used. They cannot enhance the what do you call it? They are not as efficient as direct band gap material. That's what I'm trying to tell here is doping transition metal in indirect. Transition metal plus indirect semiconductor cannot be as efficient as band gap. Doping transition metal in direct semiconductor. I hope you understand. Okay, so these are just impurity. You can dope in indirect as well as direct band gap semiconductor, right? We are talking about in indirect. Okay, so if you're doping in indirect, what will happen? Usually when you're doping the these transition metals like iron, nickel, cobalt, usually all the D block elements, you get the energy level within the band gap, and that means you're creating the localized energy state, and that means you're creating a, what you call it, Same idea. Okay, you are changing the carrier dynamics, recombination process, emission characteristic. You're also modifying electrical conductivity, luminescence, though the impact is really low, negative luminescence. That's why we don't use them. This transition metal, we don't use them for LED. Okay, because this doping will not enhance luminescence, but it will reduce it. But this transition metal can be doped in other semiconductor, and they can give you magnetic properties for spintronic application as well as photocatalytic. So those who are in research, they know that doping in zinc oxide is your oxide semiconductor, right? You can dope this transition metal in zinc oxide, and you can get a more photocatalytic, means sensing application. You can use it. Okay, sensors. Okay, so this kind of application that you can generate the magnetic semiconductors, okay, by doping manganese, cobalt, iron, and then you can use it in a quantum computer or for the quantum computing or for the spintronics. This transition metal impurity with the indirect semiconductor. Okay, I mean the first type is transition metal doped in group 4 semiconductor, means कौन वाला silicon group वाला, right? काशी जी Shankar Pauche, right? So your silicon and germanium is the typically the indirect band semiconductor. If you dope in this transition metal in indirect semiconductor, you won't get much good luminescence. That means LED properties, but you get a magnetic semiconductor, you get a enhanced electrical conductivity, you get a enhanced photocatalytic catalytic ability. Okay, okay, that's it. Now there is another type of transition metal that you can dope inside a direct band gap semiconductors. If you dope transition metal in direct band gap, like cobalt in gallium, gallium arsenide, gallium nitride, indium phosphide, what you are doing is you are not only introducing magnetic properties like modifying the spin, as you are also enhancing the luminescence. So that is why gallium arsenide is the direct band semiconductor. It can become a blue LED if you dope it, if you dope the transition metal. That was the invention. Okay, now transition metal can be doped in other direct band gap semiconductor, which are second sixth group. Okay, they are CDSC or ZNSC or zinc selenide or cadmium selenide. You can also tune the optical emission, for example quantum dot laser photodetector. These are the applications. Okay, now there are direct wide band gap semiconductor, wide band for some zinc oxide, titanium oxide. They are used in sensing application or photocatalytic applications. There also you can do the transition metals. I hope you all understand how doping is done. What are the different examples? What is their applications? What is their effect in the property like magnetic, optical emission, what do you call it, photocatalytic sensing. Okay, all these I have covered. Now I hope if they will ask any application question on what do you call it, optical properties like luminescence, you won't be able to miss it. Okay, that was the overall idea to give you. I will share this in drive. Okay, so please read, and at least read 1 to 2 times. You note it down, short notes. Okay, you revise it. That's it. Okay, if they will ask any question on this, you'll be able to uh, track it. Okay, that was the overall idea. Now I'm gonna go to the next question. If there is any doubt, I'll take it at the end. Okay, I hope I have not missed any concept. Okay, so you can pause this video and you can read this. Okay, so of course. Okay, so as per the concepts that we learned, okay, so it's very obvious that for LED, what is the material required? Okay, so you cannot go with indirect and transition metal. This is typically they will give you very less efficiency because of that phonon that is involved. Okay, the phonon that will the transition will not have that much energy because it will lose the energy. So that is not the case, and of course you can use this for spintronics, for solar cell, for other applications, but emissions of light, it's not good. Indirect with without any impurity, it is anyway not good. So we got indirect with the isoelectronic impurities. So this isoelectronic impurities can enhance your emission by creating by helping to generate the what do you call it, a particular tune the band gap or wavelength. If you can tune the wavelength or band gap, you can get the light, because you can bring this EG in within the range of particular lambda that can give you the from 300 to 700. That is the visible light. That is where we need the emission of light or LED. Okay, that you can do, that we just learned. So this is the true, and of course direct band gap is one question that is already there. Okay, now next question is Which of the following is true for TG? TG का definition क्या है? Below TG, material will become viscous. Obvious है. And at TG, glass transform from amorphous to crystalline. That is not true. Okay, TG is not for the amorphous to crystalline transition, but TG is from the soft to hard, glassy to soft, rubbery transition, right? So this is not true. Soft, rubbery, we also call it viscous. Okay, viscous effect. So this is the transition that we have, glassy, amorphous to the soft, rubbery or viscous. TG is dependent on the heating rate, of course. We are going to see TG matters, okay? Because if you change the heating rate, the heat flow will be different in your DSC curve, right? You'll get a completely different curve. Okay, and if you're getting the complete different curve, your TG will be different, right? So this curve are affected by heating rate, just like the TGA curve that we learned. And below TG, nucleation and growth takes place in glass. That is wrong. Below TG, everything is freezed. Everything is freezed. It's a glassy. There is no diffusion at all. There is no atomic diffusion at all. If there is no diffusion, how the nuclei will form? Embryo and then nuclei. If there is no nuclei, how the growth will occur? So this is stupid, huh? So it's this, and this A and B is a uh, answer. Next is very interesting question. So Frenkel and Schottky. What is Frenkel definition? By definition, Frenkel is your positive charge will go in the interstitial. That's it. And what is Schottky? One positive and one negative together will go out of it. So for example, you see here, one positive is missed here, and one negative is missed. Sorry, negative bigger. One negative is missed here, and one anion is missed here, and one cation is short here, right? So it's a Schottky. In that case, this is neither Frankel nor, because bigger atom is missed. There is no smaller atom mix or cation missed, right? Means there is no cation vacancy. So that is, it's not Schottky. So you can use your common sense, right? Here also you see it's a typical Frankel because one cation from this place went to the interstitial. Okay. Now this is the very interesting question. Okay, so if you see this curve, you think like, oh my god, I don't remember my first order reaction rate and its equation and formula. How will I able to solve it? Then if you see this option, by seeing option you realize, oh, this is nothing but Arrhenius equation, or very similar to my diffusion equation, right? D equals to D naught e to the power minus q by kt, where my ln d is plotted with 1 by t, and I get something like this. This equation is very similar to Arrhenius equation where rate is decided, right? Right? Your rate constant k is a e to the power minus q by kt. Is it different? No. It is exactly same as diffusion equation where k is your rate constant which changes with t. Okay, so here comes the mathematics. One form of the ln k versus 1 by t is mathematics. How to get that mathematics? K equals to a ln minus q by kt. Usually people write activation energy E. But that's okay. You can write E, A, whatever. U, K, G, जो मर्जी लिखो, okay? Sorry, ln क्यों लिखा? A e to the power minus q by kt. Okay. Now, how to plot ln k versus 1 by t? You have to convert ln k. So ln k equals to ln a and plus ln e to the power minus q by kt. Right? Now, you can simplify it. Ln k equals to ln a plus this minus q by at will come down, right? So it becomes minus, let me write plus minus q by kt. That's it. Ln E is just 1, right? Ln E is just 1 because base is also E and E is also E. So ln E base E is 1, right? Or log 10 base 10 is 1, right? So our final answer is ln k, just like diffusion we have learned in test series, no? Ln a and plus, you can write minus also, no? Q by kt. So if I'm writing this as y and this minus q by k as, this is c and this is my m and this 1 by t is my x, then I can plot y equals to mx plus c. It's a linear where my x is 1 by t, where my x is 1 by t, and my slope is negative. My slope is negative. Means it should not go like this. It's a positive slope. It should go like this. Okay? You can plot it also. You can solve it also. You can find the negative intercept. क्या जानना है भाई? Let's say this is 10. Let's say this is 2. Let's say this is 4. Let's say this is 8. What is my slope? Perpendicular by base. Perpendicular is 10 minus 2, 8. Sorry, final minus initial point, right? Final point is this and initial point is this. So final value is 2 and minus initial value is 10 and divided by final value is 8 and initial value is, how the final initial is coming? I'm moving towards the graph. I'm moving towards this way. So it's the same thing, okay? So you'll always get negative. Let me tell you, huh? So 8 minus 4. So it's a minus 8 by 4. That is minus 1 by 2. So slope is negative. That's it. So that's why so this value will be exactly equal to minus q by k. And that is how we find the activation energy of diffusion, right? If you remember. So this is one graph that you can plot. Another graph is ln k wala, this is correct, okay? And another graph is this, okay? This is also true. How come it's true? Because it's exponential. What is this? Is exponentially increasing. This is exponentially decreasing. This is exponentially decreasing. This is increasing, then decreasing, but okay. So this curve is e to the power x. This curve is e to the power minus x. Very simple. Okay. Now why this curve is exponentially increasing and this curve can be the answer of because it is directly t. So k is a e to the power minus q by k into 1 by t. Okay. Now this 1 by t, I want to write t. How I can do that? So if it is just t, k equals to a e to the power minus q by k. If it is just t here in the numerator, forgive me, it is not correct. Okay, I'm just giving you. Then it is exactly same as e to the power minus x, where my x is t. Then I would have got my graph like this. This graph is e to the power minus x, where this is my x. But actually it is not just t, e to the power not t, but it is e to the power minus 1 by x. So if you, this is the I have learned in my 12th when I was preparing for JE, play with the graphs by Arihant application. And that book was so beautiful. They have given, like, if you have a function like y equals to f of x, your f of x could be anything. How you can plot a graph? If it is y equals to mx, what is the graph? This is the graph. If it is y equals to mx plus c, depending on whether it is positive intercept or negative intercept, you're getting this is the graph, or this is the graph. If it is sinusoidal curve, what is the graph? If you shift by, if the sine x is, this is the graph. If it is sine x plus 50 degree more, then how this curve is shifting? Okay, so there are many things that is involved, but I, at this gate level, I won't suggest to read all those play with graph, but at least the formula that you know in your gate exam preparation, you should know how their graph is plotted, right? This is the understanding you have to develop, otherwise it's difficult, right? So this, if it is e to the power minus 1 by x, then this will become exactly reverse of this. It's not as smooth, but it is shown. It is shown. Okay, so let me show you a slide. in the Wikipedia page. Okay, so I just told na. Uh, I mean, you might think, sir, how will I remember this? Whether this graph will go this way or this way? See, there will be always one or two question in your gate exam where you feel, okay, I don't know this answer, and it's it's completely okay. It's fine to leave one or two question. Everyone is not genius, okay? It's not simple. So if you see all the solutions, you will realize that you can easily achieve. If I can achieve 35 marks because I, okay, I am nobody, okay? So but you could have easily scored 32 to 33 marks. That how this paper is. You can leave this question, but still you can score 30 plus marks, right? But you should give a try. You should understand each and everything, okay? So it's okay to leave some questions. Some questions will be tricky. So in all the practical cases, ea will be always greater than rt. Okay, so that is one thing that you need to remember. And this is the typical things that we just learned. This is the graph, and this is a typical graph that we get for this reaction. NO2 equals gives rise to NO plus O2. This is a typical equations, and this is the graph. It's easy to actually solve this also if you have a calculator. I mean, let's say, for example, if you are a mathematics, okay, if you prepared your JE, even though you don't remember this graph, you can find out it. Anyone tell how? Anyone of you can tell how? Anyone? Come on. How to plot k versus 1 by t? How to plot k versus 1? How to plot k versus t? You make a, you make what? You make a k and t table. You put k equals to 1. I'm really sorry. Yeah, it's correct. No, you pay input and output table. K is your output, t is your input. This is your y, and this is your x. Right? You put t equals to 10 degree in what? In this equation. You find out this as just one. You k equals to a equals to 1, e to the power minus. Ea is just take just any constant number. Let's say 1. But this should be ea should be greater than rt. Remember. So you take some bigger number. Ea some take like let's say 1,000. So that your r is 8 and t is your, let's say, 10 degree. So the 80, so ea will become greater than the 80. So let's take 1,000, and then let's take one constant, and then your r is just 8.314 multiplied by t. You put t equals to 1, 2, 3, or let's say 10, 20, 30, 40. Where? In your virtual calculator. You'll find your k is, let's say, 2. Then your k will become 4, 3. Then your k will become 6. Then your k will become 9. You can find now in your gate calculator. And the moment you plot at this temperature, I got this. At this temperature, I got this. At this temperature, I got this. And you plot, you'll get this. It's very simple, right? So you could have found this answer if you have time in gate exam. If you have, the function and you want to know the plot, you can easily plot. You have to just take x-axis as input and y-axis as output and find out all the values. Okay, so it's not so tough. Remember, but okay, even if you would have skip it, it would have not mattered. Okay, because paper was so easy. Because coming next questions are so easy, you cannot even uh, imagine, huh? So the another one is a CVD. So if you have simply read my notes given in your test series notes, okay, that I've given in the drive, or if you're my regular students, then you got a complete notes on this crystal growth or thin film deposition, okay. But if you simply open that, if you would have simply opened that what do you call it, notes, you would have simply found out this all options. It's so simple. Okay, it's so simple. I cannot even imagine. Okay, so let me open my what do you call it, PDF, the notes that I've shared to you all, right? uh, the PDF that I have shared to you all, the material science gate MST, right? This PDF that I've already shared you to you all. um, yeah, okay, so you can, I'm just giving an overall idea. Okay, so let me go to the question. So I will read that question. That statement is already there. Okay. So if you see, just open the what do you call it? Uh, 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 our test series notes. Okay, you simply open the CVD. The first page, itself gives the whole answer. You don't need to go anything. That 2 marks question was based on just first page. Okay, this is a CVD. It is saying how the CVD is done. How CVD is done? You generate the gas. You introduce the gas in the chamber. You activate it by decomposing it using heat or plasma. So it's nothing but a decomposition. That gives your first answer. That gives your first answer. Your source material is vaporized and thermally decomposed. See, you don't need to do any rocket science. Okay. Now, okay. Now, if you go, okay, if you go and see the concepts of CVD, so what exactly you're doing? You're bringing the reactive gas. You're activating it by decomposing it. Okay, and by decomposing it, and then the decomposed either a byproduct as well as the reactive gas. Byproduct will be removed, and reactive gas will come. It will start nucleating, and it will diffuse. It will start nucleating, and after that, it will give a layer with simple nucleation growth concepts. Okay, that we have learned. Okay, now we see the same thing is happening here, right? Pyrolysis. What is pyrolysis? You're decomposing. For example, you have AB gas. You're decomposing to A solid B gas. B gas will be removed, right? And this solid will be deposited. Very simple, right? The same idea is happening. You can have SiH4. You are decomposing it at 500 600 temperature. Now silica is solid. It is getting deposited on the substrate, and this is a gas. It is removed, right? We have a silicon deposition using CVD. It's not rocket science, right? That is one thing. Second thing is the quality of thin film. That is the second option. Okay, how does the quality? Usually the thermal PVD, the physical vapor deposition or thermal deposition, you see the quality is very poor. Density is also very poor. So by default, CVD will give the good density. This is the question. Okay, see, CVD will give the good density, good hardness. Grain size is finer. If finer the grain size, harder the material. Do you agree with me or not? Hello? If grain size is finer, material is higher, yes or no? Material is harder and stronger, yes or no? Using Hall-Page equation, right? So finer the grain size, excellent the hardness, excellent the density. That was the question. More is the isotropic. Every direction property will be same. From this table, it was asked. Okay, so this notes was given last year as well, but maybe student just didn't care to think about what is the quality of deposition that we get, right? So that is something that you need to understand, right? I mean, you have to read. I have already given the material. You have to read. Okay, so that's it. So this is the answer. Okay, source material needs to be priced, and second is suitable for preparing film of high density and uniform thickness, uniformity and the density. That's it. Okay, so that is even tukka maar ke bhi guess karke bhi you can find out, but that's the different thing. Now come back to this amazing question. Huh? Oh my god, this question can be also asked in gate. I can't even imagine for 2 marks. See, these people have given you the electrical conductivity sigma. They are asking actually aluminium are sorry electrical conductivity, and electrical conductivity is given 3.8 into 10 power 7. Remember the unit. Okay, if you cannot focus on unit, you may do the blunder. Okay, so this is ohm and meter. You don't need to see everything, just in what unit each is given. Ohm and meter, all are SI unit. Okay, so ohm meter inverse or maho meter. Okay, and then your mobility is given by 0.0012 meter square volt second inverse. Everything is in SI unit. Now they're asking to calculate the density of electrons per unit meter. That is N. N is how much? In integer you have to calculate, and the charge is also given. Oh my god, 1.6 into 10 power minus 19. So what is the formula? Sigma equals to ne mu. That's it, khatam khel. Mu is in the SI, and E is in SI, sigma is SI, so n will be in SI meter. You'll get your answer within 1 minute. You can solve this question. Okay, I don't need to solve it. Okay, you all know how to solve it. Next question is from my notes directly. Okay, so my note says कि this fixed steady law diffusion or fixed first law is only applicable in very thin sheets or very thin membranes. Even this example is for the membranes only. Okay, thin plate. So you have a different concentration or partial pressure, and depending on that you get a equation. You get a concentration gradient, so delta C by dx, where this is C2 minus C1, this is dx is just thickness of the plate. Okay, and to permeate there will be a net flux flow, and that flux flow is called diffusion rate, is called how much material amount or content, which is unit of atom per meter square second, that is m by at. That is my flux. Okay, that is my flux. So my flux is what, how much amount is diffused across certain area, how much amount is diffused across certain area per unit time. Per unit area per unit time is my flux. That flux or diffusion rate is decided by first law of thermodynamics. J equals to that flux will be decided by not steady state diffusion first fixed law, d dc by dx. That J can be decided. Okay, so if you see this, you see the unit. Okay, the J has the unit of let's say moles or atoms or kg. Everything is just amount, right? So kg. Okay, and then kg or moles or atoms, it's okay. You can always convert kg into mole, right? And mole into atoms. How? Arey bhai, what is the definition of mole? Kg you can convert into number of mole is weight by molecular weight, right? So you have a kg, you have a molecular weight fixed constant, you can find out the mole. You can always convert. No, it's just and one mole has n number of atoms. You can always convert. Okay, let me give you one thing. Let's say I have a 10 to power 24 atoms per meter square per second. I want to know in kg. Let's say my atom is hydrogen, and let's say my क्या बोलते हैं कि that's it, and its atomic weight is 1. Atomic number is 1. Weight, what is atomic weight of hydrogen? 1, right? Hello, because there is no new there is no what you call, there is electron and the okay, whatever. So yeah, so idea is you have atomic weight 1. Okay, now hydrogen has atomic weight 1 AMU or 1 gram per mole. Okay, so you can convert into kg per meter square. Kg, how? Because your this many atoms you convert into mole. So mole is how much? Mole is how many atoms you have divided by, let me write 12 into for my simplification. So divided by Na. Number of atom divided by Na is your number of moles. Yes or no? Because it's a unitary method, no? So it's a 2.30 6.023 into 10 power 23. So it's nothing but 6 से 6 cut gaya, and 10 power 24 20, it's a 10. So you have a 10 mole. So this atom is 10 mole. So you got a 10 mole. Simple. So you can find out mole per meter square second. Now if you want to know the kg, you want to know the kg per meter square. So what is the mole? Mole is weight by molecular weight, right? So your weight is mole into molecular weight. Simple. How many mole? 10 mole. And what is the molecular weight? 1. So you have a 10 kg. So this is 10 kg per meter square second. So you got my point. You can always convert atom into mole, mole into kg, because they are amount. They are a quantity for amount. Okay, mole, kg, atom, all are amount. So that's why don't blindly see, oh, I have atom, this question is given in kg, how can I solve? Oh my god, this is not that way. Okay, so now so that is the idea. Okay, this is the fixed first law that you have to apply. This is the concept of J that you have to apply. That is kg per meter square second. Of course, you can have mole or atoms, all are same. And then dc is just depending on the unit of dc, you get the unit of j. So if the dc is in kg per meter cube, that's why your unit of j is kg per meter square second. Okay, I hope you understand. Now let's go to the question. If you see the question, this is the question where it's very difficult to solve actually. I feel very, because if you don't know how to apply the concept of in units in the question, it's difficult to solve this. Okay, otherwise it's very easy because they have only played in units, nothing else. So what they have given is, they have given that this area is 100, I mean 1000 mm square. That gives you straight away, uh, that gives you that gives you 1000 multiplied by 10 to the power minus 6, right? 1000 multiplied by 10 to the power minus 6. Okay, meter square, that transfers to 10 to the power minus 3 meter square. The thickness is 2 mm. So my dx is, how did I know whether it is a, because I know it's a membrane, it's a diffusion, it's a diagram is also given. So it's a simply steady state diffusion. Okay, so dx is 10 to the power minus 3 meter square. Now, okay, so hydrogen concentration maintained. Okay, so CH and Cl. So this CH I can write as 1 and I can give it 2. So my DC is C2 minus C1. Okay, that is how much C1? 0.3. Okay, whatever, that doesn't matter. Huh? It's a difference. So 1.5, 1.5 minus 1.3. Actually, it is 0.3 minus 1.5. Actually, you'll get a negative value. Okay, you'll get a negative value of 1.2. Okay, but in, that's okay, it's okay, let it keep it negative. Okay, c1 c2 minus c1. Now it's asking rate of diffusion, that means capital D. So you have j equals to minus d dc by dx. You already have dc, you have dc dx, you want to calculate d, but you don't know j, right? So what is my j? J is my mass per unit area per unit time equals to minus d dc by dx. Now, if you see carefully, they are asking in kg per hour. Okay, in kg per hour. And area is already given. What does that mean? Kg per hour. They want to calculate. Okay. They want to calculate the kg per hour flux rate, J. That's the flow. Okay, J is nothing but flux, kg per hour per meter square. But they are telling, don't take per meter square, you can multiply this meter square. I need just kg per hour. They are asking calculate J, not D. I'm really sorry. Just asking to calculate J, and D is already given. That means saying to calculate m by t only, kg per hour only, you can take this A to this side as per unit, right? So they are telling to calculate m by t, where minus d, you can take A this side, A dc by dx. See, by seeing the unit, you will know it is not just j, it is not just m by 8, it is only m by t. Guys, it's very important. Okay, otherwise you cannot find out m by t, you will say only j, you will not use d to multiply it. Okay, first thing. Second, does it dimensionally it makes sense? So let's see. So your m by 80 equals to minus d dc by dx. It's very easy question, only play with unit, nothing else. Okay, so your m by 80 is kg per meter square into hour. I'm assuming everything is hour here, and your d is meter square per hour. How did I know? You have to know, guys. Yeah. Meter square per second is the unit. Okay, leave it. So you know very well, right? D equals to root x equals to root dt. Of course, it's never equal, it's proportional, but you can write equal k. K is a constant number, right? So x is in meter. So you can write x square equals to dt, right? Of course, k. So unit of x d is x square by kt, right? That means x square is meter square by t is hour, right? Meter square per second or meter square per second. K has no unit, okay? It's a constant. So meter square per hour. I'll write meter square per hour or meter square per second into, you see, every unit is kg, C is kg per meter cube. So it is kg per meter cube divided by x is meter. Does left hand side becomes equal to right hand side? If yes, then so kg per hour you want to calculate. This meter square come here. Okay, meter square will come here, and then you already have meter square per hour multiplied by kg per meter cube by meter. Now if you see, if you solve all of them together, you will get the kg per hour. Left hand side is already there. Okay, if you solve all of them, you'll get kg per hour. So dimensionally, it's okay to find out kg per hour. Only you need to transfer this meter square to this side. That is the only idea. Nothing else, guys. Nothing else. It's just a common sense. Unit methods. You have to understand the units of each. So you might think, sir, I didn't remember the unit of J. Oh my God, how can you don't remember the unit of J? You know the formula, right? J equals to m by 80. Find out from this. No need to remember J, okay? But you have to use the aptitude, okay? Simple. So m by t you want to calculate, right? D is given, A is given, DC is given, DX is given, minus is already there. This minus will nullify this minus. So you can simply write m by t equals to, even you can write minus, doesn't matter. Okay, T, D, A, DC by DX. Your D is already given. See the also unit of D, guys. Unit of D. This is also a trick. Everything in hour, I put no D unit in meter square per hour, right? It is given in meter square per second. So I should write here D is given, which is 1 into 10 power minus 8 meter square per second. I'll convert into per hour. So 10 power minus 8 into meter square, and second is nothing but 1 by 3600 hour. 1 by 3600 hour. How did I know? Arey bhai, you can know 1 hour is 3600 second. So 1 second is 1 by 3600 hour. So I have to divide the value by 3600 to get the hour. That means this is going to multiply. So it's a 3600 multiplied by 10 power minus 6 meter square per hour. I can put here D in meter square per hour, A in meter square, DC is 1.2, right? And dx is 2 mm. I have to put in mm, right? And I'll get my answer. Very simple. Okay. Only thing is you should know it's asking m by t. That's it. Okay. Otherwise, it's not possible. How could I know the rate of diffusion purification? You might think that it's a diffusivity or it is a diffusion rate. It is a D. But why this D is given? No, the rate of diffusivity. How did you know? Rate of diffusion rate is J, not D. By seeing the unit. Your D unit is meter square per second or meter square per hour. It will never be kg per hour. That means they're asking m by t. That is a flux. Okay, that's it. Next question is even more easier. Actually, it's not easier, but I feel like in my test series, the first open test series that is free to all, the question is based on this only. And it has been given from last 3 to 4 years, right? If you know different theta value, how can you find out HKL values? Or how can you find out which crystal structure is this? Or how can you find out A? Or how can you find out missing theta? It's not a rocket science. Okay, so let me, so I have already noted down all the theta values. So in some more crude way, what it's saying is it's a FCC, and you draw the theta, and then you find out the sine square theta. Why, I'll tell you. And then you find out the ratio or individual value. What is that? I'll tell you. Don't worry. Theta is your 21.65. So it's a corresponding sine. You find out the sine square, sine theta means sine 21.65 from calculator. Then you square it. You'll get the sine square theta. That is 0.1361136. Forgive me, I've already calculated before. Now this is the 25.21 degree. You find out the sine theta of it, then you square it, you'll get a number of 0.181422. Okay, then you find out, always write more than 4 place. Okay, don't write 2 or 1, because the higher the places, more will be, lower will be the what you call it, error. Okay, because every time you calculate sine theta, you leave few numbers, right? So that creates the error. Now next angle is 37. Its corresponding cos square sine square theta is 0.363188, and then you have a x then its corresponding sine square will be sine square x, and then you have a 47.58. Okay, that corresponding sine square theta is 0.54. Okay, 496. Okay, now what I have taught you in my test series, okay, in my regular batch, in my class, okay, I have already taught you that sine square theta ratio is exactly same as h plus k, h square plus k square plus l square is directly proportional to sine square theta. Means whatever the ratio of h square, k square, l square, it will be exactly same as sine square theta ratio. How did I know? From the Bragg's law. Okay, so lambda equals to 2d sine theta. So your d is 2a root h square plus k square plus l square sine theta. Now I want to calculate h square k square, so I'll take it out this side. H square plus k square plus l square is 2a by lambda sine theta. Now you square both sides. H square plus k square plus l square is 4a square by lambda square and then sine square theta. See, a is a constant, lattice constant. It's a constant value. Lambda is a fixed X-ray wavelength that we are using for my testing powder method XRD. Okay, so these are all constants. So h square plus k square plus l square can be written as sine square theta. What does that mean? If the ratio of h square, k square, l square is 1, 2, 3, 4, 5, my sine square theta ratios will be also 1, 2, 3, 4, 5. Individual value, if the individual value of h square, k square, l square is 3, 4, 8, 11, 12, individual sine square theta value will also will be 3, 4, 8, 11, 12. Okay, this is the idea that we use to find out which now even with this data I could have already asked without giving FCC. Without giving FCC, let me tell you, this has made it very easy. If it is not easy, no, it's very, if it is not given FCC, then also you can find out FCC. How? So in FCC, what is the ratio of h square, k square, l square? 3 is to 4 is to 8 is to 11 from the extension rule, right? 12, 16, right? The h square plus k square plus l square ratio. You can find it in any book. Huh? Okay. Now, individual value, because each number is not, there is no common in all, common one value in all. You can find out individual h square, k square is same. Individual means first peak will be sum of h square, k square plus l square exactly same as 3. That is 111. My h is HKL, first HKL is 111, my FCC. So if you square h square plus k square plus l square, you get a 3. If the second HKL is my 4 का मतलब क्या 200. Second HKL is my 200. So individual number is 2 square plus 0 square plus 4. What I'm trying to prove here is there is a ratio, there is an individual. By individual, you can know कि my 1, 2, 3, 4. My fourth pick will be 11. Fourth pick will be 11. It's very simple. Same. So 1, 2, 3, 4. Fourth pick is 11. In this case, in this particular scenario, my individual value ratio is same as individual because there is no common. For example, in BCC, what is the h square plus k square plus l square ratio? Ratio matlab proportionally they will increase or decrease. Ratio is 1 is to 2 is to 3 is to 4 is to 8, something like that. But individual number for each peak, individual h square plus k square plus l square number is 2, 4, 6, 8, 10. So what is happening is, so individual first peak is 2. That means h square, k square, HKL is 110. If you find out h square means 1 square plus 1 square, it's a 2. The second peak is giving you 4. H square, k square, l square is 4. What does that mean? That means second peak is 200. What is third peak? Third peak will give you 6. That is 211, right? H square, k square, l square. That you cannot find out from ratio. For example, if you find out fourth peak, one, if it is BCC, and then if I did 1, 2, 3, 4, you say 4 is from ratio, 4 is 4. Fourth peak is ratio is 4. But the fourth peak exact individual value is 8. So individual value say you have to calculate, not the ratio. Sometimes value ratio both is same. For example, this ratio is 3, 4, 8, 11, 12. Why this becomes different? Because in the value 2 is common. 2, 4, 6, 8, 10, 2 is common. You can take 2 as a common, then ratio will become 1 is to 2 is to 3. You got my point? So the first way is to see if it is FCC. So first peak, second peak, third peak, fourth peak. Fourth peak is 3, 4, 8, 11. Fourth peak 11. That means my this value corresponding h square plus k square plus l square value is 11. That means my sin square theta value should also be 11 from this concept. कैसे पता चला? How did you tell? I mean, how can you tell? It's not possible. No. There is some direct release. Actually, if the individual values and if the individual value and ratio value are same, I'm again repeating it. If the individual value and ratio is same, then every h square k l square value will be exactly same as every sin square theta. मतलब कि you can write sin square theta for fourth peak exactly equals to 11. Even though it's a value of h square, k square, l square, you can write sin square theta equals to 11. You can say, sir, in that case, h square, k square plus l square is exactly same as sin square theta. हाँ भाई, because it individually they are same. Okay, let me prove it. Let me prove. So you can simply put sin square theta equals to 11 and you can find out what is theta. This is your answer. So sin square theta, if you are at my level, that you know that h square, k square, l square fourth peak ke liye 11 hai, so my sin square theta will also be 11. Okay, and then you can solve. If I will be the aspirant and I'm solving in the exam, I'll directly put sin square theta equals to 11, even though I know h square plus k square plus l square is 11, not sin square, because both are proportional, not same. Since this individual number and this individual number, kahan gaya? This individual number and ratio both are same, I can write sin square 11 as well as same. But in BCC, I cannot write. Okay, but I'll show you from the calculation. So from theta directly you can calculate. You can directly calculate. You'll get 44 point. How? First you find out sin theta, that means root 11, and then your theta, that is sine inverse root 11, and that you'll get a 44.947. But you might be thinking, sir, in that FCC case, sin square theta is exactly same as the h square k square for particular peak, and you calculated it. I agree, but if FCC is not given, then sir, if this FCC is not given, and then you have to find out. So you don't know whether this fourth peak is 11 or as per BCC it is 8. As per SE, it is 1, 2, 3, 4. It's a 4. Don't know, right? H square, sin square theta value is, right? So in that case, okay, so you might be thinking, sir, in FCC case, individual values, fourth individual value is 11. So I can write sin square theta equals to 11 or h square plus k square plus l square equals to 11. But in case of BCC, if it is fourth peak, what can I write? You can write individual values like sin square theta, not ratio, individual values equals to 4. Sorry, 8. Individual value is 8, no? Fourth peak. First, second, third, and fourth peak. What is this peak? What I'm talking about? Okay, I'm talking about this peak. Okay, I hope you understand what I'm talking. This is first peak. HKL, this is at theta 21. I'm sorry. इसका twice करना पड़ेगा. You have to twice of it, then it will become 2 theta. This is 2 theta. So twice means for some 42, 40. This is 43 degree. This is first peak. Then you have a second peak, third peak. I hope you understand. Okay. So individual value you can directly put sin square 8 and you can find out the theta, not the ratio. How exactly it's happening? Okay, let me show you. So if the BCC FCC is not given, then also you can find out. I've already taught it in my test series. Okay, I hope you all know. Kaise? So see, focus here. Okay, so I know my sin square theta, and sin square theta ratio is exactly same as h square k square l square ratio, right? So how can I find out the ratio? You can find out the ratio by making this as suspect. I mean, there's two ways. Let me tell you the simplest way. I'm suspecting that my first sin h square k square l square should be 3. Second will be 4. 3, 4, 8, 11, and 12. Because I'm assuming it is FCC. Okay. Individual ratio of sin h square k square l square ratio will be this only, no? This we already know, right? Now, so can I make this number as 3? How can I make this 3? So I want to 1.136136. I want to multiply by how much to get 3? So I have to find out the factor. How can you get n? N is this I want to make 3. So multiplied by how much into 3? I can get 3. So I can, let's say n is the multiplication factor. So n equals to 3 divided by 0.136136. I'll get the factor 22.04041. That means if I multiply by, this is my n value, huh? So if I multiplied by 22.046 in first number, it will become 3. I will multiply. What is the ratio? In ratio, I can multiply the same number in everything. Ratio will not change. You got my point? Just like BCC. If I'm writing 1 is to 2 is to 3 is to 4 is to 6 is to 8, like 3, 4, 5, no, 5 is not there. 5, 4, 4, 6. Yeah, okay. So you can multiply this whole ratio by a number, but let's multiply by 2. So 2 is to 4 is to 6 is to 8. You can multiply by 10. 10 is to 20. It won't change. Or if there is an individual number, 1, 2, 3, 4, 6, 8. Okay. I can multiply by a common number to make it a ratio. That is the idea. So individual number, I can make it a ratio. How? By multiplying by a factor. Okay. So you multiply this to this number, it will become exactly 3 because we use the 3. Now you multiply the same number with this number as well. It will become 3.998615. That means automatically it has become 4. If you multiply the same number with this, it will become 8.00483116. Means automatically it will become 8. I have not given that. I just made first 3, other automatically sets. Okay. If you, now ultimately, if you multiply this by 22.04, I'll get 12.01111 something. So I'll get 12. That means if you multiply the same 22 with this, I should be getting 11. Right? So in that sense, forgive me, why I found out this 22.047, because I wanted to show ki if you write this if the h square, let me tell you, h square plus l square ratio value a particular peak is 11, you cannot write directly sine square theta equals to 11. That was I wanted to write. I first told you can write sine square theta equals to 11. Now I'm telling you have to write multiplied by a constant k. Either multiply here or multiplied by constant k. Why? Because you see your sine square theta, your h square, k square, l square is directly proportional to sine square theta, right? Is directly proportional to sine square theta. So if you want to remove the sine proportionality, what you put? H square plus k square plus l square, you put equals to, I'm repeating it again, equals to constant k into sine square theta. So for the fourth peak, if my h square, k square, l square individual value is 11, so I can put here 11 equals to constant k multiplied by sine square theta. So you cannot directly put if h square, k square, l square, let me tell you, because they were the ratio, there was a missing constant. H square, k square, l square is exactly 11. You cannot write sine square theta equals to 11, but a constant k into sine square theta is 11. Because they are proportional. The moment you remove the proportionality sign, you can put equal and then you can put a constant k. You need to find out that k. This 22.04 is the k. So for example, if I multiply this number with 22.04, I got 8. Similarly, if you multiply this sine square theta with 22.04, I'll get 11. That is the only idea that you have to follow. Okay. So I hope you all understood. Sorry for this mess up, but I hope you understand it. Okay. So you cannot put directly equals to, but you find out this factor. So this factor 20, so that what I mean is this you can find out by 11. You don't know 11, no? So you multiplied 22.2 everywhere. Here. So you multiply 22.0404 into this sine square, because you multiplied everywhere sine square, and you'll get 11. So 22.04041 multiplied by sine square x, this value you should get the 11, because everything is just set up 3, 8. It's a equals to 11. Now you can find out your x. Sorry, sine square रहेगा. You can find out x. Your sine square x is somewhere 1 by 2. So your x will be somewhere your 45. You cannot directly write sine square theta equals to 11, because h square, k square, l square ratio is proportional to sine square theta. H square K square individual value is proportional, not equal. To put equal, you need to find out the K. That is the way. Now I will tell you, if FCC was not given, okay, if FCC was not given, but still you can find out it is FCC, because all other ratio automatically becomes 3, 4, 8, 11 if you multiply the factor. Okay, so I hope you all understood that if you this sine square theta, you have to make 3. If automatically this is not coming 3, 4, 8, this is of course unknown, and 11, 12, if automatically not coming, it is not FCC. If it is coming 1, 2, 3, 4, then it could be simple cubic or BCC. Then some, because in BCC also you get 1:2:3:4, and a simple cubic also you get 1:2:3:4, and this is the ratio, not a individual value. This is the ratio, not an individual value, because we are dividing each number by a factor, so they are ratio, not individual value. So if you are getting 1, 2, 3, 4, right, then it either could be, it is a ratio, H square K square L square ratio, not the sine square theta ratio is exactly same as the H square K square L square ratio. So they are the ratio. If you are getting 1, 2, 3, 4, 8, then it is either it is simple cubic or BCC, because both has the H square K square L square ratio, that is 1:2:3:2. Individual value of BCC is 2, 4, 6, 8, 12. I hope 10. I hope you understood. Okay. So in that case, A is given. Let's say 1.3 angstrom. Then you can find out. Assuming let's say this is SC, then this peak will become 100, right? This will become 100. Now you know the HKL, right? You know the HKL, you know your A, you know your theta, you can find out the what? A value. And that, so because your lambda equals to 2D sine theta, you know your theta, right? And you know your lambda, right? I know your HKL because you assume it is SC, and let me take this first peak as 100. Then you can find out the A. This A should match with this given A in the question. Now, if you are assuming it is BCC, then first peak shouldn't be 100. First peak will be what? Because individual value is 2, 4, 6, 8. So what is the first peak? Even the ratio is 1:2:2. Individual value is 2, 4, 2, 4, 6, 8. So what is the first peak? Because H square plus K square plus L square is 2. What is the first peak? HKL 110. Because then only you can get 2. 1 square plus 1 is 0. So now you put here, if you SC, it is not SCA is not matching, then you take first peak as 110. First peak as 110. Okay. And now you know HKL, you know your lambda should be given in the question. You know your lambda, you know your HKL, you know your theta, this theta you can use. You find out the A. If it is matching with the question, then it is BCC. But for the case of FCC, it is not, ratio is individual number. Ratio is individual number, right? See, your ratio is 3:4:8, 11, and individual number is also. What does that mean? That means, for example, in a simple cubic, it is 1:2:3:4. So from based on this, you cannot find out HKL. If it is BCC, the ratio is 1:2:3:4. Then from this, you cannot find out the HKL. From this, you will get 100. But in BCC, the first peak is 110. That is wrong, because in BCC, ratio is 1:2:3 for H square plus K square plus L square. But individual number for each peak is 2, 4, 6, 8, 10. This says exactly how much is the H square plus K square plus L square for first peak. This says how much is the exactly H square plus K square for second peak for BCC. So when you're finding the HKL, you should find out the individual number. But ratio is helpful. Why? Because it is exactly same as the sine square theta ratio. So if you're getting 1:2:3, 4, that means it could be either SC or BCC. I don't know about the individual peak. I have to assume whether it is 1:1:0 or 1:1:0. Whether individual value is 2 or individual value is 1. Okay. But in case of FCC, you don't need to know the individual value, because peak is ratio is individual value. Ratio is 3:4:2, because there is no common. Okay. And individual value is also 3, 4, 8, 11. So first peak, either you choose from ratio or either you choose from individual. It's the same. So here, if you're getting 3, the ratio, because you have multiplied by the factor 22, if 3 by default, automatically, if it is coming 4, if it is coming 8, if it is coming 12, then by default this is 11. because it is already given FCC. If it is not, this everything is matching, yeah. So you need to find out how much you have to multiply in this to get 11. So how much you have to multiply into this to get 3? How much you have to multiply in this to get 4? It's a simple mathematics, right? It's a simple mathematics. It's a simple mathematics. So I hope you all understood. Okay. If you have any other doubt, please let me know. I'll explain in great detail. Okay. I'll go. This question I already discussed in the test series also. Okay. So you can do this. Okay. Now let me remove all of them. Okay. And then let me remove all of them and then explain. So what I'm trying to tell here is you have a theta. Okay, you find out sine square theta. Let's say your theta is 21.65. You found out sine square theta 0.136. Now you have to make it either 3 or 1, depending on the since it is FCC, you have to make it 3. How can you make it 3? How much you have to multiply it here to make 3? So 0.1361136 multiplied by how much? You can get 3. I'm intentionally making it 3 because it should come 3, because my ratio for FCC is 3. Sine square theta ratio or h square k square L square ratio is 3. So that means I can find out my factor 3 by 0.13611, and that is 22.04. Now every theta I know, sine square theta, I keep multiply. I will automatically get 4. I will automatically get 8. Here it is x. Sorry, here this is x. So this is my sine square x. Then I know if I multiply that factor 22 multiplied by this number, because I multiplied by this, I got 4. I multiplied this, I got 3. Similarly, I multiplied this with this, right? I get 11. So my factor 22.044 multiplied by the value of sine square x should become 11, and then I get my x. Okay, this is a simple idea. I hope you all understood. Okay, next question is just what do you call it? Uh, see, so what is given? EF is given 0. Sorry, VF is given 0.4. That means VM is my 0.6, because total should come 1. And modulus of composite in longitudinal direction is asking even in GPa, and EM is given as 6.9 GPa. You don't need to even worry about unit. And EF is also given 69 GPa, and they have given such a simple number so that your calculation will become so easy and you'll get your answer. So your E1 is EF and plus EM. Okay, so it's so easy. You just get your answer within seconds. Okay, only this sine square theta question, no, I have already given this in my notes. I have already given in test series. If you only theta is given, you can find out which if it is FCC answer, then which crystal structure is this. You can find out what is my A. Lambda should be given for that case, huh? A, and otherwise whether it is SCC or BCC, I can find out because I know my sine square theta, right? I can find out. I can intentionally make it 1. Then it will, if it is next become 2 or 3 or 4, then it is either simple Q or BCC. If it become 3, 4, 8, 11 by multiplying some value to this. Okay, how to find out that value? I have already given you. This multiplied by some value should come 3, and then you find out that this value. Then you keep multiply everywhere. You will get your exactly automatically will fit up. Then it's a FCC, and it was a simple question. Okay, I hope you all got it. Okay, so we have finished this first paper. So if you're watching and you have not joined our test series, you can join next year, and also you feel free to get 100% scholarship and join the regular batch to understand everything. Okay, I'm going to upload this video in the YouTube, and just let me know in Telegram. Just just connect with me using WhatsApp. I'll be giving contact and everything in description. Okay, thank you very much.